We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRAE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRAE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRAE helps formalize industry codes and standards. ISHRAE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRAE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRAE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRAE organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, ISHRAE India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision makers in the industry. The ISHRAE exhibition is now growing from HVAC&R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry, all at one location. Our chapters organize several other popular events like ISHRAEConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A-Quest, a prestigious quiz competition organized by ISHRAE to catalyze the transformation of the budding engineering professionals. ISHRAE provides a platform to potential employers to select student members for careers in HVAC and our industry at the ISHRAE Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of ISHRAE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. ISHRAE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation to enter and explore the universe of the Indian HVACR industry. Log on to ISHRAE.in that unfolds a panorama of information. Let us engineer a sustainable future together through ISHRAE. Welcome to Fusion Industries Limited. Water and air is lifeline in every field, and pipe is the media for transportation. Fusion. Think of quality, think of Fusion. Fusion is one of the leading manufacturer of complete range of plastic pipe and fitting for all domestic industries and agriculture. Fusion stands as the most trusted and reputed brands in piping industries. Fusion is involved in manufacturing almost all kinds of plumbing pipes and fittings. PPR pipes, fibertherm pipes, CPVC pipes, PVC pipes, UPVC pipes, SWR pipes, agri pipes, SWR pipes, ring fit SWR pipes, and column pipes and fittings. Quality is an integral part of our commitment to world-class product here at Fusion. We practice continual improvement to achieve customer delight by providing customer-centric, timely and qualitative plumbing solution through the fusion of technology in mind. All pipes and fittings are duly tested as per ISI standard, and we ensure quality products to valued customers. Fusion having enough stocks of pipes and fittings for fast delivery as per the requirement of our customers. All range of products. PPR pipes for portable water, hot and cold. PVC pipes for drainage, sewage and agriculture. SWR pipes for sewage system. CPVC pipes for hot and cold drinking water. UPVC plumbing pipes for cold water. Column pipes for submersible pumps. And all fittings. Our valued clients: Honda, Maruti, JB Group, JCB, Radisson, Pepsi, Gillette, and many more. Certification. Fusion is the registered brand of Fusion Industries Limited since 2004. Our all pipes are ISI certified and having many approvals from government and institutions. Think of quality, think of Fusion. Fusion Industries feels proud to introduce and innovative products Fusion PPRC FR composite pipes for compressed air. Fusion Fibertherm composite for airline pipes keeps air clean, right up to the point of use. The middle layer fiberglass reinforced within the two layer of PPRC acts as an agent to reduce extension capability and product durability to high pressure at high temperature. Fusion Fibertherm composite pipe having many advantages over aluminum and GI pipe. Advantages: jointing system, Fusion socket welding 100% leak proof, negligible friction loss, 0.1 micro RA value ensures negligible loss. High pressure resistant fiberglass reinforcement composition with polypropylene can withstand high pressure of up to 20 kgf. High temperature, due to fiberglass reinforcement in middle layer, can withstand high temperature as 100 degrees Celsius. Fusion Fibertherm pipe, the innovative all-rounder which revolutionized the plastic pipe industry, made a name for itself within very short span of time that stands for highest quality and outstanding ecological properties. Fusion Fibertherm is multi-layered with fiber reinforced and UV resistant. That makes it mechanically stabilized through a fibertherm mix integrated in the middle layer, and outer layer is resistant against UV sun rays and inner layer is PPR food grade material. Application: portable water, hot and cold, cooling and chilled water, HVAC and air conditioning, chemical and acid, hydraulic oil, pressure up to 20 kgf, geothermal application, recycled water. TNA of Fusion Fibertherm. We have a qualified and technical team to serve better products. Now we are showing Fibertherm blue pipe installation process for airline. This is compressor of 100 HP. Now we are connecting Fusion Fibertherm pipe 90 dia with compressor. This is 90 dia pipe. There is one bend with elbow 90 mm. Now we are reducing pipe size from 90 mm to 63 mm, with reducing T90 by 63 mm for making loop 63 mm. This loop is suspended through fixing clamp. This is quick assemble bracket for drop line, then fixing clamp, then coupler. Now fixing clamp is suspended with threaded rod. This is threaded rod further connected with beam clamp, and finally beam clamp is fixed with angle. It can be fixed with channel and can be fixed with a gutter. We are coming back to 63 mm loop, and for reducing size from 63 to 20 mm by male threaded adapter. Further, this is 20 mm drop line. Now again, male threaded coupler is fixed with 20 mm pipe for jointing ball valve ½ inch, and then pneumatic stud is also fitted with ball valve for connection of PU pipes. Finally, we assemble pneumatic drill and pneumatic instrument with all PU pipes. Now all pneumatic instruments are ready to use. Now we are showing Fusion socket welding 20 mm to 63 mm. Handy spider machine for socket fusion welding 63 mm to 160 mm. fusion butt welding machine, 200 mm to 315 mm. Think of quality. Think of fusion. Thank you.
Am I audible, sir?
Yes.
Okay. So thank you very much, all the attendees, for joining the session, all the panelists. We are very thankful to you for joining the session. As we know that today we are going to cover two topics. That is, first one, enabling healthcare facility to operate in a carbon neutral future. And second one is piping and hydronic system, both by our expert speaker, Samta Bajaj ma'am. This program is sponsored by Fusion Pipes and Fittings and supported by Women ISHRAE. So we are thankful to Fusion Pipes and Fittings and Women ISHRAE as well to support this program, to conduct this kind of programs where we need helping hand, and Fusion Pipe and Fittings is working on that also. So without wasting any more time, I would request our program chair, Valliullah Sidki sir, to introduce the speaker, Santa Bajaj ma'am, for this day.
Hello.
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 Yes, sir.
Can
You
you
are
hear me?
audible, sir. I request you to introduce the speaker, being SOP
Okay.
for this
Okay.
program.
So can you hear me now? Can you hear me now?
We can hear you, sir. We can hear you.
Okay. So thank you. And I would like to welcome all the delegates today for today's knowledge session. Our sponsor for the day-to-day Fusion Industries and Shri Pushpendra Singh Gautam ji, today's speaker, Madam Samta Bajaj ji, and all other panelists on the today's knowledge sharing platform, today's online platform. So today's session, we are going to cover two very important topics. One topic, the first topic will be the enabling healthcare facilities to operate in a carbon neutral future. How we can, what measures we can take to enable our healthcare facilities to operate in a carbon neutral future. And this will be the first session, which will be about 1.5 hours. Then the next session we will be covering today's topic of piping and hydronic system design. So these two topics will be covered by Madam today. She needs no introduction. I think everybody knows her, and she has so much knowledge that any time, anywhere, whenever we discuss with her or we ask her any knowledge on the HVAC, so we get all in-depth knowledge from her. So we'd like to give a brief detail about ma'am. She is a founder and principal consultant of Envirocon Engineering Services, which is an MEP design consultancy firm, and she has a specialization in the HVAC system. She has done from B from Delhi College of Engineering and ESMP from IIM Ahmedabad. She is also co-program chair today, also, and this for Delhi chapter of ISHRAE. She is a CWC member, ISHRAE Delhi chapter. 32 years experience she has in HVAC industry with diverse experience in HVAC system design and retrofits, which covers hospitals, commercial buildings, residential buildings, large airports, hotels, multiplexes, shopping malls, various pharmaceutical industries, clean room jobs, industrial and process projects, applications, smoke management systems, and green buildings. Also, she's in a specialization in indoor air quality upgradation also. So she has worked with leading developers in India like DLF, Max Healthcare, Airtel, Bharti Realty, HSCC, Rights, Ansels, M2K, MR, MGF, Omax, and other big names in government also like DSIDC, CPWD, Airport Authority, M3M. So as far as you know, most of the people in this industry, everybody knows her, and the knowledge she carries is going to, you are going to get enlightened. But each and every session, each and every knowledge session that she covers, we get immense knowledge. So I'd like to, without wasting any further time, I'd like to ask ma'am to uh, please take it from here and start the knowledge session.
Okay, good afternoon, everyone. Thank you so much, Siddiqui ji, for such a kind and generous introduction. In fact, it's my pleasure to be conducting this session here on behalf of ISHRAE Delhi chapter. And foremostly, I would like to thank all participants for attending and joining this session today. So I'll just like to share my screen. My screen is visible to all?
Yes, ma'am.
Okay. So friends, for quite some time now, we've been talking and we've been hearing about the terms like sustainability, sustainable buildings, green buildings, net zero carbon buildings, net zero energy buildings. In fact, it's almost 7-8 years we have been talking about these terms. And as per me, these are all synonymous terms because the goal is same. We have to protect the environment and conserve the resources for future. And in ISHRAE also, as we just saw in the video, that the theme of the year is Prakriti, Paryavaran and Parivartan. But in the healthcare facilities particularly, it is much more serious because hospitals, they are intended to preserve and improve the public health. But most of the people would not be knowing that these healthcare facilities only, they are the major contributors to the worldwide carbon emissions. And basically, the large amount of carbon emissions being generated by these facilities, it has serious effects on the environment in terms of disease spread, and it is also deteriorating the air, water, soil, and soil quality in and around the hospital areas. So in most of the countries worldwide, there is a target to reduce the carbon emissions by at least 49% by 2030 as compared to what their levels were by 1990. And by 2050, all should be carbon neutral. So now it's high time that we need to strive for energy efficiency at all the stages of design, execution, and maintenance and everything. So This is my first slide. Here we see that, healthcare facilities world over, they are contributing to around 10% of the greenhouse gas emissions. They have the largest impact, which are shown in these clouds. It is basically what are the sources of the emissions of the energy that's getting used in the air conditioning, heating, cooling, lighting. And apart from that, like HVAC is our field, but the other fields also, like the anesthetic gases which are being used, or the food that is being consumed, the commuting of the public, medical staff, patients, everything. And then the down the line supply chain of the material and the waste that are generated. There are huge amounts of waste that are generated in the hospitals. All these are sources of carbon emissions. So, and it's a fact that, hospitals, they are the second most energy intensive facilities in the country. They consume around 2.5 times more energy per square foot as compared to the other commercial buildings. And in terms of quality water requirement also, they are the third most water intensive. They have the requirement, and they are using almost 570 gallons per bed per day. So water is also how it's contributed to the greenhouse gas emissions. We should not wonder on that, because the energy is also required to distribute, treat, heat or cool it. So because of that, water is also indirectly contributing to the greenhouse gas emissions. Then, as I said, that the food part, the waste generated, all these are the sources of the GHG emissions. So if you see the distribution of the sources of the carbon emissions in hospitals, it's like this, that, the medicines, medical equipment and the supply chain, has a major percentage, 20%, 10%, 8%, all these are the generators of carbon. Then we have the building energy, waste, travel, commuting, visitors. These have the balance contribution in the GHG emissions. So the concerns in healthcare facilities are that the world over, global healthcare facilities are generating around 2 gigatons of carbon dioxide each year. And this is approximately 4.4% of worldwide net emissions. And if we compare this, it is surprisingly, it is equivalent to 514 coal-fired power plants. So we can appreciate what is the quantum involved. So now, what are the reasons, particularly in the healthcare industry? It is because, the refrigerants and the special medical anesthetic gases which are used in the hospitals, they have around 100 to 1000 times more potential of global warming as compared to carbon dioxide. And you'll also be surprised to see the data that 1 kilogram of refrigerant 410A escaping, which we call it as a green refrigerant, it is equivalent to 2 tons of carbon dioxide emissions. Then the waste disposal and the air pollution, it also causes, we know about the hospital acquired infections, how the environment within the hospitals, it causes the infection, spreads the infections, and also the discharges in terms of waste and the hazardous gases. It also deteriorates the air, water, and soil quality in and around the hospitals. So now how it is affecting our global environment. The global facts are already that there has been a 0.8 degree centigrade increase in temperature as compared to end of 19th century, and around 1.5 to 5.3 degrees centigrade is expected by 2100. And this is and how it has happened, just going into the brief history of the global warming, just for the benefit of all, basically, this is the aggravation of the natural greenhouse effect, which was there basically to reduce the solar radiation that was coming on the earth, and there was more of the re-radiation. But because of the greenhouse gases, more of it is getting trapped within the atmosphere, and it is causing to the increase in the average global temperature, which may be different at different areas, and particularly it is higher in the north and south poles, which is causing large amounts of ice melting into oceans, and in general the temperatures are rising and the sea levels are also rising, which have a multitude, which have associated health effects. So this is a image from CDC, Centers for Disease Control. It shows that how the increasing level of carbon, it is causing the health effects. It's causing rising to the inner core. Here we see increasing carbon dioxide levels is it leads to rising temperatures, causing more extreme weather, causing the sea levels to rise. Then there are this central part, it shows the 8 primary global effects which are affecting the entire globe. So that is the extreme heat, severe weather, air pollution, changes and increase in the infections, and impact on the water, food, and the environmental degradation. So these are the general things. And if we come to the outer periphery, it is uh, showing the specific health ailments which are caused because of the global warming, which are all, uh, um, asthma, cardiovascular diseases. So all life-threatening diseases can also be possible with the global warming: malaria, dengue, cholera, malnutrition. So this is all documented by CDC that these can be possible because of the global warming. Particularly the people who are at more risk than others are the infants and the young children, the elderly people, depending on the age and the medical status of the persons, they are prone to getting affected by the global warming. So, as per the this data I collected from website climatecrisis.net, shows that how the global warming, it can cause extreme weather events. We can have floods at certain places and droughts at the others. We can have, it will cause sea levels to rise. It will change the amount of precipitation, change in the agricultural yield, melting of the glaciers, and also the change of direction of the glaciers. Many species have already become extinct and many are on the verge of extinction. Then increase in the range of disease vector that we are already seeing, which is happening. And in fact, I was attending one presentation in Urja Varan. One of the speakers was also sharing that, so many deadly viruses. Right now, we are already seeing the consequences of corona and its variants. But there are so many other deadly viruses which are lying just dormant under the ice. And if the temperatures go on rising and the ice melts, these will also become viable and infectious, and maybe right now we are talking of pandemics in 20 years, 50 years, they may come every year. So some predictions from the catastrophic facts of global warming could be that deaths from global warming, as per the website, it can just double in just 25 years. Heat waves will be more intense. Global sea level could rise by more than 20 feet. Droughts and wildfires will be more frequent. Arctic Ocean could be ice-free in summer by 2050, and more than 1 million species worldwide could be driven to extinction by 2050. So these are the predictions. So now this is when we are talking of, like, we have deviated by only 0.5 degrees centigrade. But what is anticipated is that it can rise to 1.5 to 5.8 degree by the end of 21st century. And this slide particularly, it shows that what is the climate risk when we talk of 0.5 degrees centigrade rise, only 1.5 versus 2, because the aim is now to restrict it to 2 degrees centigrade only, because 1.5 versus 2 also, we are seeing that, like, the extreme weather, in case of 1.5 degrees centigrade, there is 100% increase in flood risk. It can increase to 170% in case of 2 degrees centigrade. Species extinction, species also around, it will be have 3-folded effect once the temperature rises by 0.5 degrees and from 1.5 to 2. Water availability, how the urban residents are going to be affected. By 21st century, 350 million people would be affected in case the temperature rises 1.5, and 410 million may be affected if the temperature rises 2 degrees centigrade. So likewise, it's affecting all the areas, whether we talk of Arctic sea ice. They're saying that, like, with the 1.5 degree, it will Arctic will see ice-free summer every 100 years. And if it is 2 degrees centigrade, every 10 years it will be ice-free. And the population also, people will be exposed to extreme heat waves, 9%. And in case of 2 degree, it will be 28. So likewise, economic growth at 2 degrees centigrade will be much lower than at 1.5 degrees centigrade. The yield will be less, and the nutritious value of the crops that will be less. So these are all like catastrophic effects. And I mean, if we are comparing that, if it is only 0.5 degrees centigrade rise, these could be the comparison in the various areas. So it's high time that we have to have very serious concern about limiting the global temperature rise and controlling our carbon emissions. So coming to now the potential greenhouse effect of the anesthetic gases that are used in the medical facilities. Like anesthetic gases normally used are sevoflurane, isoflurane, desflurane, and nitrous oxide. So if we see this global warming potential of various refrigerants, the sevoflurane has a GWP of 130, isoflurane 510, and this is major killing. It is 2540. What is the comparison? If we compare all these refrigerants, we can easily make out that out of all these, sevoflurane that is most viable to be used, and desiflurane, it has a GWP of 2540. And at the same time, nitrous oxide is also equivalent deadly because of its atmospheric life. So once released into atmosphere, its lifetime, it will remain in the atmosphere for 110 years. So that is also again very disastrous. So what are the lessons for the medical facilities for this? That wherever possible, one should use sevoflurane only, and the desflurane should be used clinically only where clinically necessary. And likewise, N2O should also be eliminated or reduced because of its high lifetime in the atmosphere. So that I have said that the key messages for the anesthesia practices: reduce the flow rates for this, use the intravenous and the regional anesthesia. These are for the medical facilities. So now there is basically a coalition of nearly 500 hospitals called Healthcare Climate Council, who have commonly made it a mission to address the climate change throughout the world, and how they are promoting it by encouraging, advocating, and accelerating the investment in the renewable energy and the energy efficiency, and seeing that like how the all the health sector facilities, they work towards the climate change mitigation and for a sustainable and healthy future. So now, how to take action on this? If we see these are certain clouds which are giving certain goals, how a hospital facility can reduce carbon emissions. So first of all is to appreciate and understand the problem. Set the greenhouse gas goal for the hospital and the health system. Reduce the energy use or waste. So that is where the air conditioning part of it, which will be just coming in the next part of the session. We have to reduce the energy use and the waste. Educating, then the commuting part has to be controlled, food waste has to be reduced, invest in the renewable energy, reduce, reuse, and recycle, and include the climate risks we have to avoid. So basically, this is possible only once we understand that it is, and appreciate that the efforts are necessary. So what is the solution? We should target towards net zero energy, net zero carbon hospitals for sustainability. So few more things, like why hospitals particularly, they are contributing to more of the carbon emissions. It is because of the 24/7 nature of the hospital. In most of the areas, they are operating in 24/7 manner, and that is why they are contributing to 10% of the entire commercial building sector's greenhouse emissions. So there is a goal to reduce the carbon pollution of the healthcare by at least 30% by 2030, which will reduce so many deaths and health ailments. And likewise, water usage also, because of its distribution and treatment, contributes to the greenhouse gas emissions, so it needs to be controlled. Now, the most important part in the hospital being the operating room, we need to green the operating room. So how to green the operating room? It will be good information to see that, 22, first of all, the operation theaters, they consume a lot of energy in terms of the high ventilation, lighting, cooling, filtration, is all the requirement that is the from the health point of view. And then they also are the major generators of the waste. So around 20 to 30% of the total hospital waste comes from the operation theaters. And even 60% of the medical waste comes from the operation theaters. Then the anesthetics. So we are talking of the GWP of the anesthetics. So these anesthesia are also being used in the operation theaters. So like in the general hospital, around 1/3 of the hospital expenses, they are occurring from the operation theaters only. So how, just very briefly, I will go through this slide, that like how we can reduce the carbon emissions. Like supply chain has to be green, and we need to see that, because all the chemicals and the hazardous chemicals what are being used in medical instruments and pharmaceuticals, which are the associated industry of the healthcare. They are, in fact, other day we were studying this here. I studied, first of all, for the healthcare, they are contributing 10%. Pharmas are even generating more. Though healthcare, we can see physically, so many hospitals and pharma are just sitting, at one part of the country, and in very localized areas, they are even contributing more of the carbon generations. So if we relate it with the health industry, so the manufacturing and of the medical instruments, pharmaceuticals, all these are indirectly also contributing to the carbon emissions. And then the waste. So even the waste incinerators and the landfill waste that produces methane, which is again, it is a greenhouse gas with 25 times the global warming potential. So, and then around 40% of the emissions are associated with the energy that is used to process, transport, and dispose of the food and the goods that we are using. And the transportation, as I said, because it is required, basically in the for the patient, for the staff, commuting. So this transportation also needs to be controlled, because that is a in-house resource of the hospital. So if we now come to the definition of what is net zero carbon, how we say the hospitals can be net zero carbon means, it doesn't mean that there'll be no greenhouse gas emissions, but it means that it has to be into their lowest amount. And before, we should employ techniques and technologies that can capture the carbon before it's being released into the air. So, and then there is a embodied carbon also, right from the construction stage of the building up to the demolition, up to the entire service lifetime. There is a certain quantity of carbon at each stage. So we have to reduce that emission at every stage, so that the net zero carbon is the total carbon emitted minus the total carbon that could have been avoided. Now, what is HVAC's role? Now, coming to our specific field, how we can contribute in reducing the carbon emissions in the hospitals, because we know that the in the hospital buildings, or otherwise also in any commercial building, the largest consumer of energy is the HVAC system, approximately 40% in the commercial buildings. So if we see of the technological improvement in these categories, we can contribute to net zero energy and net zero carbon buildings. So it's a fact that the average healthcare facility uses around 3 to 5 times the annual energy consumption per square feet as compared to a typical commercial facility. And in the healthcare, the air conditioning has a part of 55%, whereas in the normal commercial, it was 40%. And the distribution of the other services is like this: lighting, hot water, kitchen, at their percentage of 25, 5, and 15 respectively. So how it is affecting? It is affecting higher air conditioning costs by high capital and operating costs, high power consumption, and then deteriorating the environment in terms of ozone depletion, greenhouse effect, and increase in carbon footprint. So now, before we go further, we also need to appreciate and know why is HVAC so important, and what are the critical constraints of the healthcare HVAC requirement. Because in healthcare, HVAC is not only for comfort, it's also as a part of major therapy. And there are specific requirements. There are specific requirements in terms of HVAC being providing the healing environment 24/7 operation. Then the future expansions are always a part of the healthcare facilities, hazard controls, because they have to handle a lot of hazardous chemicals, heavy air filtration, contamination, exhaust, renovations, because new technologies keep coming, new requirements keep coming. So hospitals are always some or the other part is under renovation. And infection control is also again very, very important part, because it should not happen with the person who have gone there for treatment, they are coming back with the infection of some other disease. So as a part of major therapy, we see that like the different ailments need different types of environments for quick healing. Like cardiac patients and head people with the head injuries, they require cold and dehumidified environment to maintain the circulation to enable the normal heat loss, because body is under constraint, and when the cardiac patients are undergoing procedure, their heart is not performing satisfactorily, so the environment has to aid in the release of the metabolic heat. So similarly, burn patients and the patients with the respiratory diseases, patients under oxygen therapy, they need warm and humid air environment. People with arthritis need warm and low RH, and patients with the thyroid toxicosis, they are sensitive to hot humid conditions. And otherwise also in general also Indian heat, particularly it is very you know not very healthy for the elderly or the patient. Because मैंने भी कई बार देखा है, like we go to hospital sometimes, you know, we can compare the wait area of a air conditioned hospital and a non air conditioned hospital. तो वहां तो जाके और लगता है कि नहीं और बीमार पड़ गया बल्कि in the waiting, if it is not properly conditioned and we don't get the proper comfort conditions. So then the specific needs of the healthcare special requirements are temperature and humidity, air filtration, infection control, 24/7 operation, contaminant exhaust, hazard control, high ventilation requirement. These are the specific requirements. Air filtration, why air filtration? How it is consuming to the high energy, because apart from the pre-filters and fine filters, we use HEPA filters in many areas which have very high pressure drop, 25 to 50 mm in the cloud condition. So they are the major churners of energy. Then for infection control also, we need to maintain pressurization. We need to exhaust 100% air from the negative isolation rooms. So again, that energy has to be made good. So all pressurization, even positive pressurization, if we are maintaining somewhere, we need to put in extra makeup air, which has to be treated, which has to be filtered. So that is a load on the power. So specific needs are the 24/7 operation, hazard control, ventilation requirement, and then the psychological requirements also. As I said, that healthcare, they have to hospitals. Nowadays, they have to present a positive picture of health, happiness, comfort, and care. Then only very quick healing is possible. So this is where I just, for the further understanding, I had just mentioned the departments, because in the super specialty hospital, so many departments are there which have a different application, different environments, different levels of filtration, and different levels of pressurization required. And which is why we need to have so many AHUs and small AHUs with the that is a higher power consumption area also. So we have basically the visitors in the outpatient department. Then we have the inpatients and surgeries, like operation theaters, ICUs, post-operative and wards. Then we have the administration support services like administrative section, labs, blood banks, pharmacies, mortuary, laundry, parking. Then we have the interaction spaces nowadays, mini hotels and meditation rooms. And then most of the areas, though they say that there are some areas are there which where air conditioning is essential and somewhere it is desirable, but mostly, you know, it is nowadays it's required. The comfort conditions in the extreme conditions are required. Special filtration is required in the areas like imaging and radiology and the ICU and ICCU. At least the microwave filtration is required, and operating rooms, so fourth stage filtration is required. And then we have a proper exhaust system in the sterilizing rooms, kitchens, and laundries. So now, why do healthcare facilities, again, just pondering and giving a thought to why do healthcare facilities consume so much energy? This is because of the special typical design conditions which are required as per the NABH 2018. These are the conditions for the operation theaters. For the critical class B and C or class A operation theaters, the temperature conditions stipulated are 64.4 to 75, which are quite low as compared to the normal, which will be 72 to 74, 75 degrees Fahrenheit are the normal comfort conditions. But in the operation theaters, they just want to be it to be doctors, even medical teams, so they will ask, because I have done a lot of hospital jobs. So what medical teams, they want it to be just like a cold store. They want 16 degree centigrade ki bilkul hi matlab body को जो patient's body does not have to do anything, मतलब वो एकदम ही dissipation होता रहे heat का. So for that purpose, they want extreme cold store conditions. And then other thing is that the doctors also, they when they operate the surgical team, 8 or 10 surgeons, they're the major source. They're sweating and because of the high equipment and lighting load. So to control that also, lower temperature is desired. Then we have the low temperatures in ICUs, CCUs, and the radiology machines, where so many sophisticated machines are there. LINAC machine is there, MRI machine is there. These machines have very high sensible loads, equipment loads to the tune of 15, 20, 30 kilowatt. And they also need very precise control of temperature and humidity for their work. And they are very, very expensive and sophisticated machines. And they they can operate only in the specific temperature and RH ranges as mentioned by the manufacturers. So how, if we compare this, how the hospital air conditioning is different, because hospitals normally they require very high supplier change rates. For example, 20 air changes in OTs as against 6 to 8 air changes in comfort, which is a general requirement. Even the ventilation air requirement is higher. It is 4 air changes in OTs as against 1 to 2 air changes in comfort. Humidification, we need to provide it in the winter. The RH goes too low, it will cause static electricity generation, and it also will cause the dryness of mucous membranes and low RH. So that reduces the self-immunity defense mechanism system of the human beings. So we need to maintain the minimum RH stipulated. Then dehumidification, in any case, it is required to control the RH for comfort, for infection control, and for operation of sophisticated machines, because the machines, they cannot will not function properly at very high RH. Then the stringent filtration and the fan energy requirements. We need fine and HEPA filters in most of the areas in the hospitals, and many areas are 24/7 day operations. Reheat requirements are there to maintain the temperature, and because the machines they are operating, they are not operating, processes are not on, but when we design it for the peak load. The air quantities are designed for the peak loads when the machines are operating. But when the process is not on, in that case, the RH will tend to rise. Then we need to provide the reheat. That's a continuous demand in many areas in the hospital. And the reheat, as you know, it's a parasite on the energy. Then in the hospital, another important requirement of the power consumption is the winter cooling. Many areas in the hospital that needs winter cooling also. For example, your operation theaters and the radiology areas, again, they need some cooling in the winter. And then there is a wide range of demanded space comfort. As I mentioned, by medical teams, OTs, they may ask for temperature as low as 16 degrees centigrade, as it is lower than even what the NABH has specified. The nurseries may require higher, because that is for the small children. So approximately 50 to 55% of the annual energy consumption will be attributable to air conditioning, no matter its location. The geography of the facility will not matter much, but the inside activities in the departments are such that they need these conditions. So major energy users in the hospitals are basically, it is the energies going in cooling and dehumidification, heating and humidification, outdoor air cooling and dehumidification, outdoor air, the ambient pressure also has to be heated, humidified, reheating, and the fan energy requirement. So all these are the consumers of energy in the hospitals. Now, apart from that, there are so many exhausts which are happening in the hospitals. So exhausts are happening from kitchen, laundry, hot labs, clean sterilizing supply, isolation rooms, hazardous contaminant areas, laboratories, then the dirty linen rooms, waste storage rooms, anesthesia stores. All these areas need to be provided with the exhaust. And after all, now all this exhaust has to be made good. That is through the new fresh air, and which again will has to be treated and filtered, so that will consume energy. So this is a picture showing the exhaust from the various areas, from the kitchen, from the laundry, from the hot labs, from the CSLG, from the isolation rooms, from the waste storages, laboratories, waste storage rooms, and the soiled linen rooms, anesthesia stores. So now, having appreciated the typical requirements of a hospital facility and the constraints of the hospital facility and where the energy is being utilized. Now the question comes, how can we design for more energy efficiency? So there have to be, and there are solutions for the energy efficiency. So here I have enlisted few steps, how we can, if we focus right from the design stage, how we can focus by saving energy at every step. We can, even in the bits and pieces, one, because every drop makes an ocean, and every penny saved is the penny earned. So likewise, every kilowatt saved is the kilowatt generated. So we can work towards that. First of all, aim towards a nearly zero energy building. So whatever new facilities are being made, they should focus to be the nearly zero NZEB. That means it should consume low amount of energy, and we have to focus towards using the renewable sources which are produced on site or they are purchased from the nearby. So the facilities should be extremely energy efficient. Then second is we have to aim towards a nearly zero carbon buildings. Now, how we can say what are the nearly zero carbon buildings? What are the scopes of the carbon? There are three major scopes in the healthcare facilities. Emission scopes are there, which can be enlisted to scope one, which is the emissions which are directly coming from the sources that are handled or owned by the company themselves. So these are the emissions which are released into atmosphere at the firm level. So these are basically again divided into four parts. These are the stationary combustion sources, मतलब जैसे furnaces हैं या कुछ है, which are owned by the hospital facility themselves, the heating sources or the chilling, and all the fuels which are used in these sources, they produce the GHG emissions, they are included in scope 1. Then the mobile, whatever the vehicles the company is, the facilities owning, which are controlled by the firm, like cars, vans, trucks, ambulances, and all that. So what all generations they are, carbon generations they are putting on. So that is the, again, scope 1 emission. Then this is fugitive emissions, which are the leaks from the greenhouse gases, which can be like the refrigerants from the air conditioning machines. And as we said, read that the refrigerant gases, they have a 1,000 times more global warming potential than compared to the carbon dioxide. So once any leakage happens, companies are supposed to report these emissions to the environmental agencies. And then the third is the process emissions. So like the different processes are happening. So there are carbon emissions during the these processes. So these were the scope 1 emissions. Then is the scope 2 indirect emissions, which are again owned by the building. What are the scope 2 indirect emissions? These are the emissions which were generated, or like if the energy is being generated or it's being purchased. So what all emissions that have happened as a result of that, they are getting released directly or indirectly, releasing in the atmosphere from the consumption of the purchased electricity or steam or heating and cooling. Whatever emissions are happening, they are the scope 2 emissions that are again under the control of the facility. Then is the scope 3 emissions, which are down the line, the value chain, which are the biggest greenhouse gas emission source. And in fact, these are not mostly in the control of the medical facility or any other building. And for healthcare facility, it is around 71%. The contribution of scope 1 and scope 2 will be 30%, whereas for the scope 3, it is around 71%. And so like it will include, the distribution, processing, transportation, capital goods purchasing chain, and then business travel, waste, and till the end of the line. So in this pie chart also we can see that whereas scope 1 and scope 2 have a relatively lower percentage, scope 3, that is the down the line supply chain, there is a lot of this carbon emissions. So idea is to say that like at all the fields, not only in the hospitals, but in all the fields, we need to focus towards reduction of the carbon footprint and the carbon generation. So how this net zero design can be made, and how we can do end-to-end carbon dioxide mapping by a passive design optimization, by reducing the operational energy demand, by eliminating the fossil fuels, and by trying to generate the renewable energy on site and store it where possible. So towards that effect only, there was a 26th United UN Conference, COP26 was held in 21, and the Paris Agreement was agreed upon to target, and it was a target that we have to limit the global average temperature to 1.5 degrees centigrade as compared to the end of the 19th century. And we have to reduce the gas emissions by around 59%. So that was the step 2, reducing the carbon emissions. Now LEED and BREEAM tools to make the buildings sustainable. So LEED, I don't think we need to mention more about it. We need the US Green, USGBC, which is it's a leadership in energy and environmental designs, the rating system where we during all the stages, design, construction, operation, and maintenance, we need to develop that rating system, and we have to aim towards that to make the system and the building construction, operation, and up to the end of the building, it should be environmental friendly, and the resources also should be used efficiently. So in very simple way, we can say a green building is the one which is using less energy, generating less pollution, using less water, and generating less waste. And if we go green, this is the percentage which we can save on the global level. If we talk of energy, we can save, if the buildings are consuming 45% of the total conventional buildings are consuming 45%, by making them green, we can save 50% of that. If they are generating 35%, conventional buildings are generating 35% of the total global emissions, then we can, making it green, we can reduce 35% of it. So that way, making green will save in all the aspects. Then similarly, as we talk of LEED, there is another tool, BREEAM. UK has developed that BREEAM tool, which is Building Research Establishment Environment Assessment Method. So it is also giving different weightages to the different criteria. Factors are almost same, but it's only basically UK based. So it is also giving importance to the pollution management, health, well-being, energy usage, transport, water, material, waste, and the ecology. So we need to set some target for our building to comply to these good international, national and international standards, so that we can make an energy efficient building. Now, what are the energy efficiency opportunities in HVAC? If we talk about specifically, then we can go for energy efficient HVAC design, energy efficient equipment selection, energy management system, and energy efficient operation and maintenance, efficient building envelope and space planning. You see, though I have listed down all the steps, because believe me that like if we try to save on energy at every step, then, and if we talk of a say medium-sized healthcare facility of around 4 to 5 lakh square feet, and if we are able to make it even 10% more efficient in the energy, we can reduce the energy consumption by 10%, then it is equivalent to ridding the environment of around 25,000 kg of carbon dioxide. We can say it is equivalent to afforestation of around 750 acres of land. So we cannot ignore these small parameters, and working in all the steps of design, operation, maintenance, expansion, renovations, and retrofits, which will make the system more energy efficient. Now, how can we design it for more energy efficiency? If we compare the conventional system, normally the air handling units are constant volume types, cooling heating coils are fixed discharge temperature. We are designing at 55 degrees Fahrenheit. Chill water pumping is nowadays, normally secondary chill water pump, secondary variable is there, and the primary variable also has started, but not very common it has become. Cooling tower fans are normally constant speed, condenser water pumps are normally constant speed, economizer cycles are not normally implemented, TFA units are designed for 100% pressure. So these are the conventional means of design for a healthcare facility. The first way we can think of is VAV system control to save energy, because in a hospital we have many areas which have significant unoccupied hours and where the continuous directional control is also not required, the common waiting areas or atriums and all. So there, and then there are certain areas, as I said, like the MRI or imaging and radiology areas where the sensible loads of the machines is very, very high. So because of which the design is air quantities are quite high because of the high sensible loads. So in such areas particularly, and if we, this is the data I picked up from ISHRAE, that like in hospital facilities world over, it is a average data that most surgeries, they work for around 65 hours per week. Most recovery areas, also post-operative areas, OPDs, radiology areas, they work only 8 to 9 hours per day. 8 to 9 hours per day. So they are very less constantly occupied. And even the areas which are constantly occupied, they have the loads are less. One thing is that they're not constantly occupied and the minimum air change requirements are frequent. Then there are certain 24/7 operation areas, so as to say, like patient rooms are there, ICUs, nurses station, labs, some areas of the emergency around 15 to 25%, autopsy, CSSD, nursery, corridor waiting, medical storage. So these are deemed to be 24/7 operation areas, but also like out of these also only partly, if we talk of patient rooms, only 80% may be occupied fully for the 24/7 operation. For similarly for the labs also around 50% of the labs, and likewise for the other areas. Then there are certain areas like purchasing, maintenance offices, X-rays and all these are working 8 to 9 hours per day operation. And then there are certain areas like physical occupational therapy, OPDs, cath labs. These are working for 9 to 14 hours per day. So idea of showing you this data was to appreciate that like in a multi-specialty hospital, being so many departments, so many activities, so many variables in the usage. There is so much variation in the frequency of usage and the times of usage that the variable air volume is a very good option in all the areas where it is, which are not very critical, also where directional control is not required, some pressurization or contamination problems or constraints are not there, then we can use it very easily in OPDs, in offices, in the pre-post operative areas, even in the areas where some pressurization is required, like ICUs and labs. There also we have techniques we can maintain. We can keep the maintaining the pressurization by the return air flow tracking, so that to have a different directional pressure sensor. So when the differential pressure sensor it senses that the pressurization levels are getting lost, that signal of the air quantity that can be overridden by the signal from the pressure sensor. So, and in most of the codes, in the unoccupied state periods, even NABH, it says that even the operation theater, when it is not occupied, we can reduce the air quantity to around 25%. So that is a substantial amount of saving. And then we can also reduce the airflow in the particularly the areas where the sensible loads are high. So when the machines are not running, when the sensible load is low, the airflow can be reduced in all these areas, CT, MRI, LINAC, X-rays, which are highly, housing the machines with high energy ratings. So VAV in the non-pressurization areas can be very easily used in the general patient room, general examination rooms, kitchens, atrium, meeting rooms, some laboratory spaces. So we should try using VAV systems. Then step 5 could be reset the supplier temperature to save energy. So it's a control strategy which will reduce the cooling requirement. It will reduce the reheat, particularly during the morning and evening hours. Now, normally what happens is we are setting the temperature conventionally to 55 degree Fahrenheit. Whereas if we can raise that 55 to 60 to 65, then it will reduce the chill water flow, and it is especially convenient if the system also has the air side economizer. Then raising the supplier temperature will reduce the energy substantially, and it will also reduce the reheat significantly. And then step 6 could be the adaptive comfort approach to save energy. Adaptive comfort, in fact, this has become a very uh, promising field, and it has found space. Now it's approved by NBC also, and most of the countries internationally, even they are colder countries than the tropical country like ours, but they are going for adaptive thermal comfort, which relates the inside temperature to outdoors. जैसे हम कहते हैं कि भी 24 degrees centigrade, it is not a whenever we design a building 23, 24, 22, तो ये हम लोग कह देते हैं, but it is only a set point कि we are comfortable at 22, 24. We can be comfortable at 27, 28 degrees centigrade also, because it is always relative to outdoor temperature. अगर पिछले हफ्ते बाहर 45 था, तो हम अब और इस हफ्ते 40 है, तो हम 27, 28 में भी बहुत comfortable होंगे. So the adaptive thermal approach, it relates the inside temperature to the outdoor temperature. It considers the thermal needs, and it considers the physiological thermoregulation, because body itself is it's a machine which is self-equipped for the thermoregulation. क्यों अपने आप बॉडी में होता है, जब ज्यादा गर्मी होती है तो we know its body is a heat engine. बॉडी में ज्यादा गर्मी होती है तो perspiration होता है, arteries will dilate. So these are all the automatically things, these are happening. Means body is adapted for the varied climate conditions. और जब ठंड होती है तो क्या होता है, आपकी shivering होती है, the arteries they squeeze. So that is why why that happens, to reduce the surface area from where the heat is. When the arteries shrink, the surface area from where the heat dissipation reduces. तो ये body का खुद का defensive action है. So people can also consider the clothing according to the environment, and the activity levels also. Like instead of the fixed workstations, they can have moving workstations. They should be allowed to. आजकल तो ये culture भी हो गया. Like if you talk of offices and all, they can go and sit anywhere near the window or inside the work hall. So that is adaptive. The person is free to adapt the varied inside conditions. Then we can deviate from the temperature of 22, 24 to 28 and even 30 degrees centigrade with some air movement. तो जो 18-24 का हम कहते थे बैंड कंफर्ट का, वो अब 30 डिग्री सेंटीग्रेड तक it is acceptable. It is a extract from ISHRAE standard 55 only. By जो acceptance level हम कहते थे कि when the people are all satisfied, when around 80 to 90% of the occupancy in an area, they are satisfied. If we can just bring down that percent to 70% people are satisfied, we increase the air velocity, then even this 30 degree ka band, it can be stretched by 1 to 2 degree. Air speed raises the upper limit of comfort band by 1 to 2 degree. तो हम 30 का भी 31.7 कह सकते हैं. तो जो मतलब basically by increasing the air velocity. So this is the adaptive comfort. And every 1% raising, it will reduce the energy by 4%. So we can appreciate that how like the adaptive comfort, how it can be a substantial source of energy saving in all kind of buildings, what to say of a hospital building. So how it can be a design solution for sustainability, because it can reduce the mainstream air conditioning by more than 40%. And then indirect direct hybrid air conditioning, it is a technique जो हम normal हम नहीं बात कर रहे. We are not talking of the direct evaporative cooling, which has a which has a constant that it is not very effective. It's not effective during the moist seasons. It cannot control the humidity. लेकिन there are advanced techniques which are the like indirect, where we can go for much slightly more bringing down the temperature by 5 to 6 degrees centigrade further. 23-24 तक हम आ सकते हैं, and without the direct spray of water, by the indirect exchange only, without coming in the actual contact with the moisture. So and then if you want the exact precise conditions, we can go for hybrid air conditioning. We can go for a DX or a chill water coil coupled with the indirect evaporative cooler. But we have to come out of our, first of all, mental blocks. Because normally क्या है, consultants भी है, या customers है, they don't want, these systems are slightly expensive than the normal ventilation systems, but of course less than the air conditioning. And in any case, like even if we maintain 25 plus minus 2 and the RH also 60 degrees, still their operating cost will be 40% less than the conventional chillers. So here it can minimize mainstream conditioning by more than 40% without even compromising on the conditions. So we can have units for many areas where the unit can be used on the fresh air mode. It can be used on a indirect evaporative cooling when we are not running the coil, or when we can run it along with the conditioned air IEC plus coil, and we can exhaust the total air, or we can also use it in the configuration when we are not exhausting, we are using it only as a air conditioning system whenever for 2-3 months when the outside conditions are demanding. So there are techniques possible, but we only need to explore, and we need to come out of our conventional means. Or जैसे हम ये नहीं सोचेंगे भी नहीं, हम तो बहुत बड़े consultant हैं, we will not design for ventilation, we will मैं कैसे ventilation design कर दूं? तो it's like we should go for the new techniques, and we have to see the payback period, which comes well within 3-4 years, and then there is a substantial energy savings only. So like, what are the potential application areas in the hospitals? They are the outpatient departments for the hybrid cooling. We can use it in OPDs very easily, in the lobbies and reception, in the waiting areas, in the kitchen, in laundry, in physical and occupational therapy areas, in the maintenance departments, in the wards. We can use it this hybrid cooling. Then step 7 is the humidity management without heat, face and bypass damper control. In fact, when I started my career as a trainee in Blue Star, so that time systems were designed in the fashion कि हाँ जी monsoon में आपका air quantity का requirement कम होता है, तो the consultants used to specify the bypass damper. तो उतना वो bypass damper को करते थे, या फिर मतलब we used to reduce the air quantity to avoid the reheat. So nowadays वो concept नहीं है, face and bypass damper concept I'm seeing very rarely people specifying, whereas we can control the RH by bypassing, by providing the face and bypass dampers. Then the humidity management can be also through the wraparound heat pipe system for a cooling. This thing, the heat pipe system is also very efficient. Here we have a pre-cooling section where the refrigerant evaporates, taking the latent heat of vaporization from the incoming air, then pre-cools the air, so that reduces the load on the cooling coil. And then on the discharge side of the heat pipe, here it will pick up the heat and condense, and it will discharge heat and to condense, and then this acts as a reheat for the overcooled air. So that way artificial reheat is avoided, prevented, and we can make more use of the passive means. Then step 9 is the natural ventilation of energy savings and infection control. So during the COVID times also, WHO, they have given emphasis, even CPWD guidelines, NCDC guidelines, they have mentioned that like the natural ventilation is all the more important. Wherever possible, we need to increase the ventilation air quantities. And though it has its inherent advantages and disadvantages, like though the high ventilation rates are possible, low capital cost, but the disadvantages are that not very much possible, where the ambience are very, very high, and direction control is not possible, and it will be dictated by outdoor air climate. But then we have a solution. We can again have a mixed mode type of a system. Natural ventilation augmented with the mechanical ventilation. And this is why still people are not using it, because most of the people are ignorant about its performance, it's how it will be calculated, how it has to be designed, and what benefits it is yielding. So you can appreciate that, like if you consider hospital ward of 7 meter by 6 meter by 3 meter wide, high, and where there are basically one door and one window, right? One door of 1 square meter and one window of 1.5 by 2 square meter. Then with the open 100% open window and open door, the ventilation rate, the natural ventilation, it is can be accomplished to 37 air changes per hour. With the open window 50% and open door, it is 28 ACPH. And even if we close the door completely and keep the window open, it will still be 4.2 air changes per hour. So this is without any power consumption. If we are getting so much of ventilation, we can appreciate that how much effective it will be in terms of comfort also, as well as the infection control. So there are different types of plans for the hospitals, wind-driven natural ventilation. There is a single side corridor, the cross ventilation to the patient wards. These are the promising configurations given by WHO. There is courtyard type design where combined wind and the buoyancy effect in the courtyard, the hot air tends to rise. So that kind of a design, in fact, now I have seen in a couple of AIMS applications, they are following these kind of designs. And as regards the performance ratings of these kind of ventilation systems, the hybrid mixed mode and the mechanical ventilation. If we compare the hybrid mixed mode and mechanical, then WHO for all kind of climates, ambient climates, hot and humid or hot and dry or moderate or cold, it is giving equal ranking to the mixed mode and the mechanical ventilation. That means 4-star means the performance is good both in terms of thermal comfort and the airborne infection control. So in all kind of climates, except for extreme cold, the mixed mode ventilation has a equivalent ranking as the purely mechanical ventilation. So we should try using those in our buildings. Then step 10 is some guidelines about for the architects, which we most of us know. So I will just rush very fast through this. First is the orientation. Need to orient the building towards east-west axis, because all of us know that the heat radiation towards the east and west is always more. So it should be oriented towards the east-west axis. Then the reduce the exposed area. If the building can be made in a more compact form rather than the more exposed area, it will have lesser area for heat gain. Optimal selection of the glazing, high efficiency glazing, you're using shading devices, U values as per ECBC, insulation of the walls, reducing the exposed area, increasing the internal areas, optimum wall window ratio, giving natural lighting, effective use of the insulating material like AC blocks, taking advantage of the natural ventilation means there are local currents always there. So trying to align the building towards the direction of the natural local wind air currents, cool roofs like reflective colors or the insulation, using plantation or providing vents for on the southern walls for release of heat, control of the outside microclimate by planting trees, by greenery, because that will also absorb the carbon generation. It also acts as a carbon sink, and avoid the hard paving. So these are some ways by which, if possible, the architects, they can reduce the building, make it more energy friendly by the passive means. And then for the inside layouts also, there are some considerations for the reduction in the air conditioning energy and how the architects can plan it. Then they can locate the spaces to reduce the internal loads. So the spaces or the departments where high internal loads are going to come, they should be avoided to be placed towards the south. And rather, east-west axis, since they are more attracting the heat radiation. So it is better to provide the non-critical areas like store, circulation areas, service areas as a buffer zones for the internal spaces. So that will reduce the load requirements of the internal spaces. Then similarly, open spaces, they require low loads than the closed spaces. So the waiting halls, workstations, they can always be, located towards the north side. So then the air conditioning requirement will be less. Similarly, if we are talking about the mechanical equipment like compressors or the machines, which are highly energy sensitive, they can be avoided to be placed on the south side, can be placed on the north side. That will increase the efficiency as well as the lifespan of the machine. And then while designing the ducting, also lower pressure drops, rounded transitions, provide the meters, because until we provide and we meter the power consumption, we cannot take any steps to control it. And enough adequate space for maintenance, lighting controls, and the imaging equipment also. Nowadays, it is coming with the self cooling things like MRI machines, or all these machines nowadays are come with their own chillers, so that the jacket cooling, instead of the radiation losses and the heat spreading throughout the space, and then air conditioning having to remove it, it can be a localized cooling for the machine. That those systems are also available nowadays. Then I'll be briefly mentioning about the so many active cooling strategies and technologies which are available for energy savings. There's a variable chill water piping. We all know it can reduce the power consumption by 10 to 15%. Then harnessing the solar energy, using the heat recovery wheels, we can always uh, retrieve the energy being lost in the exhaust air and pre-cool the outside air to the desiccant wheels, and it can reduce the load by 50 to 60%. We can use the airside economizer, means use the outside when the outside temperatures are favorable. We can go for free cooling, and that will save the energy of the chiller. We can use the water side economizer, that can be used even for the areas, where winter cooling is required, or for during night operation, when the outside when the wet bulb drops, and we can, and the inside requirements are also low, we can go for the reverse cycle operation, and through a heat exchanger we can use the cooling tower water only in the chill water lines, but we need to separate the open circuit and the closed circuit pipelines to avoid the possible fouling. And then the variable speed control on the fan, VFD, it has also become common. We can use that. Low approach cooling towers, making it the approach is 5 degrees Fahrenheit, will reduce the uh, chiller energy. Use high efficiency boilers, 88 to 92%. And because boilers heating, they're very much required. Use heat pump instead. Boiler economizer should be used. So what all heat is being wasted through the flue, that can be recovered and used to pre-treat the feed water, boiler feed water. And then it is also a good practice will be not to have a centralized steam boiler system, for because different areas in the hospital require heating, sterilization, laundry, CSSD, or the normal air conditioning. So it is always better, because their requirement will be different during the different parts of the year, and even during different parts of the day. So it is always better to have a dedicated this thing for the particular process, and not to have a common plant, because central plant will be inefficient during the low load conditions due to the distribution losses. And also try to use high delta T heating system. So normally 20 degree Fahrenheit, use a differential of 20 degree Fahrenheit, that will reduce the piping cost and reduce the pumping cost. Try to use variable speed even for the heating systems. Commonly what we see, that these pump ratings are small, so people normally, even the customers, they will during the cost control, they will say कि हाँ ये चलो ये VFD बता दो कितना हटता है, क्या saving होगा. But there is a saving if you provide VFD with the even with the hot water pump. Then we can also use plate type air-to-air heat exchanger for the heat recovery, and the heat pipe system, as I already covered earlier. Then in the streams, even where the cross contamination problem is there. There we cannot have a plate type heat exchanger, then we can go with the runaround loops for heat recovery. So runaround loops are basically, we can have the pipelines with a mixture of glycol and water that can be pumped, and the heat can be recovered from the outgoing exhaust stream and for the pre-cooling of the supplier. So that has a sensible heat efficiency of 60 to 80%, and with absolutely no problem of cross contamination. And then it is very much advisable that we go for a separate chiller for OT and for winter cooling, because that will be, as I said, like OTs have a special low requirement of inside temperature, and we can, if we combine it with the chiller of the entire facility, then we have to run, even when the other areas we can run at a 48-degree, 50-degree Fahrenheit chill water out temperature, we will not be able to get the temperatures in the operation theater. So then we have to run the entire facility at a lower chill water out temperature. So it is always advisable we go for a separate chiller, small chiller for OT, and that can be used even for the winter cooling. And OT plus some allied areas, radiology, they can be combined. Then selection of one chiller as a heat pump. As I said, variable condenser water pumping has become very common now. Variable primary chill water pumping can also be a good option. Cogeneration process, if the facility is large, they can think of generating the electricity in-house, and then it can be used for trigeneration, means we can use the energy, we can generate electricity, produce cooling as well as produce heating. And thermal storage, again, that is a generation of cooling or heating, and it can act running the chiller during the off tariff, when the tariffs rates are low or when the outside temperatures are lower. We can use that and store in the energy storage tank, and we can use it during the peak hours along with the main chiller. Geothermal heat pumps also are being recommended. The HVLS fans are the large fans for the waiting areas and for the high height areas. These produce a very good turbulence, and they can reduce the effective temperature by 5 to 6 degrees Fahrenheit. So they are a very promising solution in the future. And then the smart control and Internet of Things, if we are monitoring it properly, we can save the energy. And the personalized portable HVAC technologies are also there, like the personal workstations only can be cooled instead of the entire space having been cooled. Then targeting net zero with HVAC modeling, by BIM modeling, by CFD design, we can see that how the distribution or what are the temperature, what are the resultants parameters we are getting, and we can make the designs during the design stage only, so that can we can improve the design decisions. Then the modular type of systems, they are also give good energy efficiency, because they have the flexibility of operation, ease of maintenance and installation, and they can be customized for the specific work areas, and then they can also be added phase wise. So that is the advantage. Then during the COVID period only, so many active air purification technologies have come after evaluating their relative merits and demerits for our specific hospital. In fact, UV has become nowadays mandatory. We are using in most of the areas. Then similarly, ESP is also. So likewise, there are other technologies, UVGI, PCO, ESP, plasma, nanofiber, very high filtration levels. So these can also be used to improve the indoor air quality and can reduce the pressure drops of heavy mechanical filters. And we can aim to reduce the carbon footprint size. Underfloor cooling is another method where the chilled water is run in the floor in the pipes, which will cool it by convection system, and then we may not, we can run it at a higher chill water temperature, so reducing the chiller power consumption. Similarly, it can be used as a underfloor plenum. Here also high supply temperature can be given 58 to 64. So, and it also is a low pressure drop system, and we do not need to chill the upper zone. Right, then we have the chilled beams. So they are also basically the chill water pipes, which can be embedded in the structure, or they can be suspended separately. So they can also, along with the fans, by the active and passive technology, we can use it along with the TFA unit, and we can reduce on the chiller power energy. So more recommendations on reducing the power consumption is by AHU zoning as per the hours of operation, separate AHUs for the areas with the extreme cooling requirement, and the areas which require extreme cooling, they can be provided with the supplemental cooling, which can be provided with the separate DX units. And similarly, radiology equipment manufacturers, they should be advised, or if we should select the equipment which have their self-cooling equipment. Size one chiller for the winter loads, use pressure independent valves so that we don't have to throttle to balance the system, because throttling and balancing the valves and the dampers too much, that is a waste of energy. So try to use high delta T for chill water as well as for the hot water to reduce the piping and the pumping cost, and calculate the actual fan pressure, calculate the actual system head, use electrostatic filters in the kitchen AC along with the carbon. Instead of 100% exhausting, we can use electrostatic in the carbon filters. Then use hybrid air conditioning in the areas, as I said. Use good insulation material, set a temperature dead band. There should be a uh, dead band of at least 5 degrees centigrade. Means the heating should not come on till the temperature drops below 19, and the cooling should not come on below, before the temperature rises beyond 24. So that such overlaps of the heating and cooling should not be there, because this will save energy. Use mixed mode. Try to use the natural and mechanical ventilation, mixed mode ventilation, and people will also psychologically be more happy because they have more control. They have fans, they have windows, they can open the windows, and they can. So it is a psychological effect also. They become adaptable to a wide range of temperature. In the hospital particularly, we should, for the CSSD laundry, we should have the localized hoods instead of just letting the heat spread out in the entire area. Then the heat recovery, wherever possible, from the kitchen laundry, boiler, sterilization, we should try to harness and recover the heat. Provide the sub meters. And so that was the step 13. Now step 14, selecting high efficiency chillers. I'll just rush through it. We all know about it. High COPs, magnetic bearings, use of VFDs, high efficiency air handling units should be used with high thermal resistance, low leakage, VFDs, and low phase velocities. That is very important. Like if we try to reduce the phase velocity from 500 to 400, pressure drop of the filter as well as of the coil will reduce, as well as the filter performance will improve. And the system will become more energy efficient. High efficiency boiler, use gas boiler, reduce the carbon dioxide emissions, use high efficiency motor and pumps, right size the pumps. Then says step 15 is energy saving by efficient operation and maintenance. Use building automation system, which will reduce the energy by 8 to 10%. Use energy management system and optimum maintenance and cleaning, duct coil cleaning to improve efficiency, to improve the indoor air quality. And in the retrofit, we should, even if we require, sometimes we see 18, 20 years old facility, they will go for this air conditioning is not working. They will say, call me ये एचू बदल दो, मेरी coil खराब हो गई है. But what about ducting? Ducting होगा कि नहीं? एक तो working area disturb होता है, and they think that it is very cumbersome. So they try to avoid it, but that is not a right system, because there may be design mistakes, and in the new layouts it may not fit. There may be hot and cold spots, and customers, they never understand the cost of ducting is peanut. And if it is not designed properly according to air quantity बढ़ गया है, using the same ducting, that means increasing the pressure drops, causing noise, causing drafts, unbalanced air pressures. So it is always worthwhile going for a redesign of the ductwork in the retrofits rather than using the old ducting, which is dirty also, and not suitable for the new requirements. Similarly, pipe redesign can be looked into. And the lighting retrofit also, if we are able to use smart products like the sensors, LED lighting, it will save the energy by around power by around 27%, and will save the operation cost by 15%. Use of BFDs, because we all know the cubic relationship between the motor speed and the HP, and 10% reduction in the speed, it will cause 27% power reduction, 50% speed reduces 87 power reduction. So in the retrofit jobs, we can think of providing VFDs, of seeing the compatibility of the existing pumps and all, and we can use this energy saving techniques. So then the testing and balancing of the air. So we should do the proper balancing, because balancing नहीं करते और वो excessive throttling करते हैं air side पे भी, water side पे भी, so it is an energy drain. And then latest technology is the digital twins, which is the revolution, fourth industrial revolution. So here, we are using too many sensors, and even the total hospital can be digitally cloned, and hospital administrators, doctors, they get without getting actually not they get total insight into the patient health and workflows. कैसे emergency में क्या चल रहा है, like from the remote sensing only, everything can be monitored and controlled. So they and even with their previous health status, the people can be alerted at the right time and the immediate action is required. So it improves the operational costs as well as the the digital replicas जो है healthcare में, they're so it is expected that they can predict and prevent the patient emergencies. That before the thing is going to happen, they can predict it based on their uh, digital twin replicas. And similarly, like so time is not far when we'll have virtual version of ourselves, and we'll have digital tests known as simulations to find the potential health problems before they happen actually. So this is how I would say ki, we can step by step we can aim towards zero energy and zero carbon. We cannot say zero carbon, but not nearly zero carbon thing. So in today's scenario, to address the climate change, HVAC industry, we have the responsibility to make more sustainable systems and minimize our reliance on the fossil fuels to go with the new technologies. But again, it has to be a joint effort, because we at all the stages, project owner, user, building manager, or the consultants, architects, testing agencies, contractors, suppliers, laboratories, everybody needs to has a part of it. It is not a step to be taken at 1 or 2 stage level, and it has to be seen that besides the capex, we need to see the other aspects also, the environmental concerns, lowering the carbon dioxide emissions, and so that is how we can preserve the planet for our future generations. So thank you so much for listening to me. So I have just completed my presentation in this.
So thank you very much, ma'am, for completing the first session. So I think should we take right now the question answer for this session, or at the end we should take?
We can take right now question answers.
Okay. So anybody having any questions, please send your question in Q&A section. We'll take it one by one. Time being, we can take a 15-minute breaks after they can submit their question in the meantime, and after that we will take it. So time being, I mean, playing the video of sponsor for this program, Fusion. We'll reconnect at after 15 minutes. All the attendees are requested to send their question to Q&A section. Thank you.
Welcome to Fusion Industries Limited. Water and air is lifeline in every field, and pipe is the media for transportation. Fusion. Think of quality, think of Fusion. Fusion is one of the leading manufacturer of complete range of plastic pipe and fitting for all domestic industries and agriculture. Fusion stands as the most trusted and reputed brands in piping industries. Fusion is involved in manufacturing almost all kinds of plumbing pipes and fittings. PPR pipes, Fibertherm pipes, CPVC pipes, PVC pipes, UPVC pipes, SWR pipes, Agri pipes, SWR pipes, ring fit SWR pipes, and column pipes and fittings. Quality is an integral part of our commitment to world-class product here at Fusion. We practice continual improvement to achieve customer delight by providing customer-centric, timely and qualitative plumbing solution through the fusion of technology in mind. All pipes and fittings are duly tested as per ISI standard, and we ensure quality products to valued customers. Fusion having enough stocks of pipes and fittings for fast delivery as per the requirement of our customers. All range of products. PPR pipes for portable water, hot and cold. PVC pipes for drainage, sewage and agriculture. SWR pipes for sewage system. CPVC pipes for hot and cold drinking water. UPVC plumbing pipes for cold water. Column pipes for submersible pumps. And all fittings. Our valued clients: Honda, Maruti, JP Group, JCB, Radisson, Pepsi, Gillette, and many more. Certification. Fusion is the registered brand of Fusion Industries Limited since 2004. Our all pipes are ISI certified and having many approvals from government and institutions. Think of quality, think of Fusion. Fusion Industries feels proud to introduce and innovative products Fusion PPRC, FR composite pipes for compressed air. Fusion Fiber Thumb composite for airline pipes keeps air clean, right up to the point of use. The middle layer fiberglass reinforced within the two layer of PPRC acts as an agent to reduce extension capability and product durability to high pressure at high temperature. Fusion Fiber Thumb composite pipe having many advantages over aluminum and GI pipe. Advantages: jointing system, Fusion socket welding 100% leak proof, negligible friction loss, 0.1 micro RA value ensures negligible loss. High pressure resistant fiberglass reinforcement composition with polypropylene can withstand high pressure of up to 20 kgf. High temperature due to fiberglass reinforcement in middle layer can withstand high temperature as 100 degrees Celsius. Fusion Fiber Thumb pipe, the innovative all-rounder which revolutionized the plastic pipe industry, made a name for itself within very short span of time that stands for highest quality and outstanding ecological properties. Fusion Fiber Thumb is multi-layered with fiber reinforced and UV resistant. That makes it mechanically stabilized through a fiber thumb mix integrated in the middle layer, and outer layer is resistant against UV sun rays and inner layer is PPR food grade material. Application: portable water, hot and cold, cooling and chilled water, HVAC and air conditioning, chemical and acid, hydraulic oil, pressure up to 20 kgf, geothermal application, recycled water. TNA of Fusion Fiber Thumb. We have a qualified and technical team to serve better products. Now we are showing Fiber Thumb blue pipe installation process for airline. This is compressor of 100 HP. Now we are connecting Fusion Fiber Thumb pipe 90 dia with compressor. This is 90 dia pipe. There is one bend with elbow 90 mm. Now we are reducing pipe size from 90 mm to 63 mm with reducing T90 by 63 mm for making loop 63 mm. This loop is suspended through fixing clamp. This is quick assemble bracket for drop line. Then fixing clamp, then coupler. Now fixing clamp is suspended with threaded rod. This is threaded rod further connected with beam clamp, and finally beam clamp is fixed with angle. It can be fixed with channel and can be fixed with a gudder. We are coming back to 63 mm loop and for reducing size from 63 to 20 mm by male threaded adapter. Further, this is 20 mm drop line. Now again, male threaded coupler is fixed with 20 mm pipe for jointing ball valve ½ inch, and then pneumatic stud is also fitted with ball valve for connection of PU pipes. Finally, we assemble pneumatic drill and pneumatic instrument with all PU pipes. Now all pneumatic instruments are ready to use. Now we are showing fusion socket welding, 20 mm to 63 mm. Handy spider machine for socket fusion welding, 63 mm to 160 mm. Fusion butt welding machine, 200 mm to 315 mm. Think of quality, think of fusion. Thank you.
So, thank you, everybody. Ma'am, we have one question. I think it has been answered. Two questions, both the questions. So, should we move ahead, ma'am?
We can.
Yeah. So, I request you to start. Next
Okay,
session.
the second session. Okay, I'll share my screen.
Please reshare, ma'am.
Yeah, is it visible to all?
Absolutely fine, ma'am. Yeah.
So good evening again, and thank you so much for joining. And I think it's not too heavy for you to listen again from me, because I made this session specifically for fusion, because I wanted to include something of their field. So I thought I'll make something on the piping and the hydronic system design also. So in this session, in fact, first of all, I like to refresh on our fundamentals of piping and hydronic systems. And before we go into details of piping and hydronic systems, I want you to recapitulate the basic refrigeration cycle that we might all have studied in our colleges. So just to refresh it again for everybody's benefit, like refrigeration cycle, it comprises four major components. One is the evaporator. So evaporator is the area where the heat to be rejected from the load. That is the process that happens. So what actually is happening is that here the low pressure liquid refrigerant converts into low pressure vapor refrigerant so as to absorb its heat of vaporization from the load, the thing to be cooled. Now, this refrigerant now, it is a low temperature and low pressure vapor. Now, to reclaim it for use in the next cycle, we need to reject its latent heat of vaporization. And as I said, it's a very low temperature and low pressure gas. And heat normally, everybody knows it always goes from the high temperature to a lower temperature. So what is the function of compressor in the refrigeration cycle? It is to basically convert this low pressure, low temperature vapor to high pressure vapor, so that along with the pressure, the temperature also of the refrigerant can increase so that it is able to reject the heat to a higher sink. Now, in condenser, this heat, the high temperature, high pressure refrigerant, it is rejecting heat either to water or to air, whether it's a water cooled condenser or an air cooled condenser, and then it gets converted to a high pressure refrigerant in the condenser. Now, then the expansion device is the place where the high pressure refrigerant, it gets converted to low pressure refrigerant so that it gets ready for the next cycle of refrigeration. So that was something about the refrigeration cycle. Now we have two types of loops and circuits in HVAC. One is a closed loop and one is the open loop. So in the refrigeration circuit, when it is exploded view of this, we have the chiller and condenser in a cooler and condenser in a chiller. So the cooler side is a closed water circuit, which comprises of the chiller, the chilled water piping distribution system. We have the loads, the terminal units, which can be fan coil units or air handling units with their appropriate control valves. And then there has to be a pumping mechanism. So apparently this is a closed circuit. So it can be a chiller circuit or it can be a hot water circuit. So the system is that the chilled water or the hot water, it travels in the closed piping, which starts from a point and then ends in the same point. So this is a closed system. Now, on the other side of the refrigeration cycle is the open system. It is a circulation open type where we have the water cooled condenser. So we have a cooling tower, and there is a other components are the condenser water pumps. Now here this system is open because the system is open to the atmosphere at the water level of the sump level, and one at the nozzle where the system is exposed to air at the 2 points in the open circuit. So that was about the open system and the closed system in the hydronic refrigeration cycle. So now these are what are the hydronic systems, how we can define water systems that convey heat or cooling to or from a conditioned space or process with hot or chilled water are the hydronic system. So hydronic means water. So whether it has to convey hot water or chilled water from the space, or it can be a process, and it has to convey either heat or cooling. So that is basically the hydronic system. Now, what are the various components of hydronic system? As we saw, there has to be a source of, can be heat, source of heat, or source of cooling. So whether we are circulating hot water or cold water. So that can be, source can be a chiller for cold water. It can be hot water generator for a hot water. Then there has to be a load from which is to be cooled or which is to be heated. So these are the terminal units, air handling unit, and FUs. Then we have the distribution system, which comprises of the piping, right? So, and then we have the circulation pumps. So the different components, so as to sum up is the source, the load, the pumps, the distribution system or the piping system, and the expansion chamber. So there is an expansion tank in a closed system which has to take care of the expansions or contractions depending on the outside conditions. The water will be expanding or contracting. So it has to be then allowed for that expansion or contraction. And there is a small tank which is open to atmosphere. So so as to say, this closed system is open to atmosphere for a very small area, that is at the expansion tank. Then in this case, we are seeing that how water is used to carry heat from the point of generation, such as cooling coil or heating coil, to the point where it can be rejected. So this is the point of generation and this is the point of rejection. So here the heat is rejected to refrigerant at the cooler. Then there will be, we have the chilled water, which can be 45 degree Fahrenheit, normally the supply temperature from the chiller, and it returns at 55 degree Fahrenheit from the load. So this is in case of when we are circulating the chilled water. Now this is the other case. It is the hot water system where we have the hot water generator and the load which is to be heated. Then this is the distribution system with the pumps, and here the temperature range is normally 100 degree and 120 degree Fahrenheit supply and return. So here heat is rejected to the electric heaters, and here in the load, heat exchanges between the hot water and the air. The terminal, again, the terminal units are there, air handling units or fan coil units. Now, that was the closed circuit, and here we have the open circuit. This is the condenser water circuit, which is a piping system between the condenser of the chiller and the cooling tower. And this is the cooling tower sump. And we have the condenser water connecting pipeline. So here the refrigerant is rejecting its heat. The condensation is rejected to the cooling tower at atmosphere. And in the condenser, heat transfer is between the refrigerant and water. So water is used to condense the refrigerant to liquid, and it transports the heat of condensation of the refrigerant to cooling tower for rejection to the atmosphere. And if you talk of the chilled water system, then this is basically the piping system is like this. We have a mechanical plant room, which is the source of generation, where the either chiller or the boiler, hot water generator will be there. So from there, this is the high side, and in the low side we may have different blocks like block A, B, C, and D with their respective load requirements. We can have air handling units, we can have fan coil units, and then the water, hot or cold, is distributing in the closed circuit. So water is used as a carrier of heat. It is the coolant. So normally the circulating fluid is water. It is transporting the heat or cold as the case may be. And so it is called a secondary refrigerant. It is a secondary refrigerant. Now, what have to be the attributes or the qualities, features of the secondary refrigerant? Why water is being used as a secondary refrigerant? First, it is cheap, it is easily available, it is non-toxic, it is not inflammable, and the secondary refrigerant should be stable in the operating range. It should be non-corrosive to the system, and its viscosity, it should not be very much viscous. Otherwise, the pumping cost will be high. So these are the characteristics of the secondary refrigerant. Now, how we calculate when we say we design Kia system 2.4 GPM per ton, 3 GPM per ton. So what is the formula? What is the basis? Technical. It is the heat carrying capacity of piping. Like it is given by Q is equal to Q is the mass flow rate into specific heat into temperature range. Mass flow rate USGPM is the volume flow rate into 8.33 pounds per gallon into 60, that's the conversion factor, which makes it 500, and delta T. Now, this is the delta T, as I was talking in the previous session. It will determine how much water flow rate we are requiring for a particular, transmission of heat. So, if we consider this temperature differential as 10, then we have this with the 10-degree temperature differential, it works out to 2.4 GPM per ton. If we make it 8, so it is 3 GPM per ton. So we see that water requirement increases as the delta T reduces. So we should aim to increase the delta T and reduce the pumping and the piping costs. Now, in the piping system, heat transfer is purely sensible, and the heat carrying capacity for a given flow rate, how much heat that water at a given flow rate will carry. It depends on the specific heat of the fluid and what is the delta T and what is the density. So commonly used delta T is 10 degree for cooling and 20 degree, as I said, 100 and 120 degrees Fahrenheit for the heating normally we use, and for the cooling normally it is 45 to 55 degree Fahrenheit delta T. So higher the flow rate, bigger will be the pipe size. So delta T governs the economics of the hydronic system. Now, if we talk of heat rejected in the condenser, so in the condenser, it is the cooling load which has been rejected in the chiller, plus the work, the compressor has worked on the refrigerant. That work also, in terms of the energy, it will be added for the heat rejection. And this is normally a factor of 1.25. So if we talk of how much is the heat to be rejected in the cooling tower, then if 1 ton cooling capacity is 12,000 BTU per hour, how much heat is to be rejected at condenser is 12,000 into 1.25. It has to be 15,000 BTU per hour. And with the same formula, Q is equal to 500 in USGPM into delta T. If we are taking normally the delta T across the cooling towers, condenser is taken as 90 and 97.5. So delta T is 7.5, which makes the GPM as 4 USGPM. तभी हम कहते हैं कि we are designing this thing as 4 GPM per ton. If the delta T is 7.5 degree Fahrenheit. So now what are the applications of the piping system? So the piping systems can be of various types. It can be a chilled water system where it is supplying only chilled water. It can be a hot water system, or it can be a dual piping system. The same pipeline can be circulating chilled water in summer and hot water in winter. So, or it can be a separate independent lines also. Then the condenser water pipe system, which is a distribution piping network between the condenser and the cooling tower, as we saw in the previous diagrams. Then we also have the piping between, for the air washer systems also have the piping for evaporative cooling. Then we can have different processes where like there are some machines which have their own inbuilt cooling machines. Then there has to be chilled water. Maybe we may need to provide a tapping from our chiller to these process cooling machines, and there is piping system for the process cooling. Now, again, coming to the hydronic systems, it can be a once-through system. Suppose it is circulating from the river, so there is no need to recirculate. It's a once-through system. Water flows only once, does not recirculate. Say river water is circulating through condenser. Or it can be a circulating system, recirculating system, which is normally so. Like this is the condensers. water is going into the cooling tower. So water is pumped from an open reservoir cooling tower, and then it comes back to the condenser. So 4 USGPM is going, and between 90 and 97.5, and this is the condenser water return to the cooling tower, and this is the condenser water supply. So this is the open type recirculating system of the piping, open system. This is a example of a air washer piping system. We have the air washer, some nozzle or media. Then there is a circulating pump between the sump and the media. So this is the open recirculating system where water is recirculated from a reservoir to the nozzle and back it comes. Then this is the closed type of a system where, as I said, we have the cooler and the water normal, the range, the cooling range is 44 to 54 degree Fahrenheit. The water from the cooler, it goes to the various terminal units, and the system is open to atmosphere only at one single small point, which is open to the atmospheric pressure, which is at the expansion tank. So water is recirculated through a closed system without coming in close contact with the air, except at the expansion tank. So open system is the one in which water flows into a reservoir or sump open to atmosphere. This system is open to atmosphere at 2 points, at the sump and the nozzle. For example, cooling tower or air washer sumps. So these are called open systems, and they need water treatment because system being open, the atmospheric air enters, corrosion also happens, dust accumulates, and it needs to be treated of the impurities. Whereas closed system is the one in which water flow is not exposed to atmosphere, only at the expansion tank where the contact area is insignificant. So this is a closed system. So in contrast to hydraulics of an open system, in case of a closed system, now what is the difference in the closed and the open system? If we see the a cooling tower in the closed system, uh, flow cannot be motivated by static head difference, and pumps do not provide the static lift. Entire piping is filled with water. Here, I'll show you, like in this diagram, this is an open system. So when the pump is not on, this part of the piping will remain empty, and the both legs, the piping, the water in the piping will be only up to the level of the sump. So because it is an open thing, both two legs, it is the two legs of the tube that will assume the same water level. This is a uh, uh, open system. Whereas in case of a closed system, it is not so. The entire system will always be full of water. And it does open in open system, pumps do not have to provide in the closed systems, pumps do not have to provide the static lift, whereas in the open systems, pumps have to pick up the static lift, which is the height of the cooling tower. So this is the closed recirculating type, and here the total pressure at the highest point is whatever is the system pressure. Suppose it is 10 kg or 16 kg or 21 kg. So it is the highest pressure at the system. At the highest point is the system pressure plus the static height or the height of the level of the liquid in the expansion tank. And then now there are two types of piping systems. One is the direct return, and one is the reverse return piping system. So how the two functions? See, like we have this illustration. This is the cooler. This is the first floor unit. Now, what happens is that in the direct return, at the different floors, the total resistance to the water flow will be different for the different units. For example, like for this circuit, say A, B, G, H. For this circuit, what is the distance to be covered by water? It is 10 feet plus 40 feet, 50 feet plus 10 feet, 60 feet plus 40 feet, 100 feet. So it is the shortest path. It has to follow the shortest path for coming back to the cooler. Now the unit on the upper floor, it has to add up this another 20 feet. So it has to travel extra it has to travel 120 feet. Then at the unit at the highest level, it has to still travel extra 20 feet. That is 140 feet. It has to follow the longest path. In the direct return, the thing is that they have to travel different they have to overcome different resistance. So the flow at the farthest point may not be here, the water flow may be optimum or even more, and here it may be less. So it is not a self-balancing system. So the demerits of the direct return system is that the flow path resistance is unbalanced, and the shortest path will receive more flow, longest path may starve. So, and balancing is possible. Normally, what we provide the external balancing valves at the inlets of all these, but still balancing is also not 100% perfect. And normally nowadays, nowadays, so it used to be very, very effective and very meticulously done. अभी आजकल तो इतना balancing करते भी नहीं है, लेकिन उतना हो भी नहीं पाता है because of the system pressures. Still there will be a differential in the resistances. So it is better is to go for a reverse return system. Is another system where the unit which is getting the first supply, it has to travel the maximum path, and say for this circuit A, B, it is also returning for the first in the first way only. Then it comes like this. The total distance to be covered is 10 feet plus 40 feet, 50, 60, 70, 100, 140, and plus 150. So total will be 150 feet in this case. So likewise, in the others also, it becomes one floor less. So it becomes 150 feet. So all the units with the reverse return system, they will follow the same path, equal distance. All parallel paths are equal. So that makes it self-balancing. So the merit of the reverse return system is that self-balancing. Only demerit is that it consumes extra pipe length and is slightly expensive. And this reverse return system is specifically recommended for large systems. Suppose it's a multi-story, 25-story building. So naturally, without the reverse return, either we have to have a reverse return. Nowadays, automatic balancing valves are also available, which do the automatic, which are not dependent on the manual balancing. So either we provide the reverse return, that is a foolproof method, and high-rise buildings, or otherwise if it's a wide corridor, multiple rooms, as in case of a hotel or hospital with corridors are there and so many fan call units are there, then also the system tends to become imbalanced. So we need to provide this reverse return. Then we have the two pipe system, which is where piping can be common for chilled and hot water. It can carry either chilled water or hot water, and the pump and coil is common. So in summer, it will carry the chilled water. In winter, it will carry hot water, but the simultaneous cooling and heating is not possible. And in the second part, we can have a separate system. We can have a separate like cooling. This is the pipe system where cooler and hot water generator are in parallel, whereas the pump and the coils are common. So the same can be used alternatively depending on the seasonal changeover. And in case of four pipe system, we have independent two sets of piping. Chilled water piping system is separate, hot water piping is separate. So we can have the independent and simultaneous cooling and heating and all the time. And it may be required in hotel industry where some guests may be requiring heating, some may be requiring cooling, or the hospitals. So it can be, but it is an expensive system because the piping cost is almost double. So four pipe system has separate piping circuits, coils, pumps, and expansion tank, and it is used for jobs which may need simultaneous cooling and heating, or critical jobs like hospitals, pharmaceuticals. And four pipe system is very expensive, so it is not normally used for the normal jobs. Now, what is piping distribution system? So we have the pipe, fittings, and valves which are interconnecting various systems and the components. And the piping system is distributing the water flow to the various components between the chillers, cooling towers, and the AHUs pumps. So this is how this piping is connecting. We have the valves, we have the pumps, we have the fittings. So what are the elements which are going into the piping systems? We have pipes, fittings, elbows, tees, reducers, valves, strainers, pumps, right? So how we select the pipe size, what are the parameters for designing the pipes? We need to know the flow rate. We have to find out the pipe size. We need to fix up a pressure drop. What is going to be the pressure drop from the source to the destination, and an amount of pressure drop. It depends on basically the viscosity of the fluid which is to be pumped. And for example, ethylene glycol will have more friction loss. It also depends on the roughness of the internal surface, what kind of pipe it is, whether it is of concrete, hume pipe, MS pipe. So obviously, like the materials like concrete and hume, they will be much more rough. So than the conventional steel pipe. And the length of pipeline also it will determine what because that depends on the layout and what velocity we want to keep on in this. That also depends on number of factors because high velocity it will cause erosion of the pipe. It also causes the more scaling and noise parameters also because of the moving water. Pressure drop also will increase with the high velocity. So we need to see what is the system pressure and accordingly velocities have to be settled. Now, pipe is sized from the pipe sizing charts, which are specific to the material of pipe and for the surface roughness. It also depends on whether the system is open or closed. As I said, like for the open system, there are more likelihood of scaling and corrosion. So the pipe sizing includes those aging factors. And normally, if you see the pipe sizing chart, even in carrier, this for the same flow rate, pipe size for open system is little over the closed type. And if it's a copper piping, it needs to stay clean throughout its life. So this is a snapshot from the carrier. This how the closed piping is designed. It is against the flow rate, and we can read the pipe dia for a given flow rate and water velocity. This is 2, 3, 4, 5, and the pressure drop. So normally it will again depend on the application, what velocity and what pressure drop we have to keep it. Pressure drop normally it should be below 5 feet, and velocity is also 3 to 4, maximum 8 FPS in the headers. And then there is also a resistance added by the fittings, and they are depending on the nominal size of the bore and depending on the type of fitting, there is a equivalent length which is added to the friction loss. So this is a fitting loss in equivalent feet of pipe. So that needs to be added. Similarly, for valves, there is a chart for different sizes and for different types of valves, we need to add in the equivalent feet of pipe while calculating the pump head. What is the recommended water velocity for various services? For pump discharge, it should be 8 to 12 FPS. For pump suction, 4 to 7 FPS. For drain line, 4 to 7. For header, it can go up 4 to 15, though it is mentioned, but we normally do not exceed 8 FPS. Risers also 3 to 10, normally up to 3 to 8. So pipe size should be sized for a pressure drop not more than 5 feet. 5 feet is the maximum, because as if we go on increasing the pressure drop, ultimately then it's churning more energy from the pump. And water velocity also for the smaller pipes, normally it should be kept less than 4 FPS. So pipe fittings such as elbows, tees, valves, they offer a greater resistance to flow than the straight pipe. So इसलिए normally जो thumb rule होता है वो क्या करते हैं, thumb rule we should not use. We should try to find out the exact routing of the piping and calculate it instead of modulating the valves later. नहीं तो chill water में like there are so many fittings and so much equivalent length has to be added. The total pressure drop in the piping, it is almost double of the straight length piping because of the fittings. So this additional pipe, it is considered by adding a resistance equivalent to certain length of the straight pipe, which is called the equivalent length. So as we saw in the previous chart for the fittings and for the valves. Now the piping material for the water duty, it is normally in air conditioning, it is MS, black steel, and it is up to 150 mm dia. It has to conform to IS 1239, and for 200 mm dia and above, it has to conform to IS 3589. For chilled water, hot water, and condenser cooling, black steel MS is specified. For drain, galvanized steel GI is specified. And though copper, it has a better corrosion resistance, but it is very expensive. So it's only used in the refrigerant pipes. And working pressure and temperature are very, very important in pipe selection, because if we are talking of a high-rise building, 25 floors, 30 floors, so all the components, whether we talk of chillers, heat exchangers, walls, strainers, coolers, condensers, pump casings, they have to be selected for that much working pressure. So अगर आपका 20 story का building है, 10 kg आपने pressure ले लिया, तो तो वो जो है वो लीकेज होता रहेगा, तो इट विल नॉट बी एबल टू होल्ड द स्टैंडिंग प्रेशर एंड the it needs to be designed for the building pressure. If the pump casing, cooler coils and all, they have to be PN16 or PN21 rating as per the height of the building. Now, if we see the IS 1239, so it is giving the three classification of pipes, light class A, class B, class C, in order of increasing thickness. Class A is the lightweight. It is not normally used only for the pipe supports. It is used. Class B also medium weight, not normally used. Thickness कम होती है तो इसकी pitting और इसकी life भी कम होती है. So normally, like for the air conditioning duty, it is heavyweight class C pipes are used, and then pipes again they can be seamless where there are no joints, or there can be ERW, electric resistance welded, where which has a longitudinal pipes. Then this is for the pipes up to 200 IS 12 up to 150 1239 is applicable, and IS 3589 is applicable for pipes 200 mm diameter above, and standard pipes are available in the length of 6 meters. And जो pipe भी है वो हम करते हैं, basically select all other factors have to be seen as the corrosion, safety against the bad quality water, underground application, and the thickness of the pipe can also be calculated. There is a formula. This is the formula TM is equal to PD by 2AC plus A. ये क्या है basically formula where TM is the minimum wall thickness. TM is the minimum wall thickness. कितना होना चाहिए पाइप का thickness. P is the internal pressure. क्या pressure उसको withstand करना है in PSI. P is the pressure, और ये जो भी हम diameter select कर रहे हैं in inches. S is the maximum allowable stress. What is the allowable stress that the pipe has to overcome? This is the corrosion allowance. A. E is the joint efficiency. तो joint efficiency seamless के लिए 1 और ERW के लिए 0.8 लेते हैं. So based on that formula, we can also calculate the pipe thickness required. And if the inside pressure is higher, the wall thickness needs to be higher. And water quality, if the water is more prone to corrosion, we need to keep a higher thickness. And type of pipe, if it is seamless or ERW, again that joint efficiency changes. So all the parameters remaining same. In case of seamless pipe, obviously if the joints are not there, the pipe thickness required is less than the ERW pipe, but seamless is expensive, so normally it is not used for HVAC systems. And for chilled and condenser water piping, ERW class C pipes are used. Class A is not used, but only for the supports, and for the drains normally class B GI pipe is used. And then we come to the pipe joints. What the different types of joints are available for the piping. They can be threaded, normally for the galvanized pipe, welded for chilled and condenser water MS. They can be flashed wherever we have to connect the equipment and valves with the piping. So we need to have flanges. They're recommended so that during maintenance they can be opened and the thing can be serviced. We have the unions for small diameter galvanized pipes, and these copper pipes particularly, they don't go for welding and all. They have to be soldered or brazed. Then these are we are showing here the different type of fitting, the welding and the flanges, welded or the threaded flanges. Then the other component in the hydronic system are the control valves, which are used across the fan coil unit or the air handling unit to vary the water in response to the changing load. So there are three types of valves, basically control valves. These can be three-way motorized valves in mixing duty, three-way motorized valves in diverting duty, and two-way motorized valves. So normally जो जहाँ पे common constant pumping होती है, variable pumping नहीं होती है, वहाँ तो three-way valves use होते हैं. Where variable pumping is used, there two-way valves are used. So ये कैसे है? Basically now if we talk of two-way valves also, three-way valves also, they are available in two configuration, mixing and diverting. ये वाला है आपका three-way mixing valve. इसमें क्या है कि this is our coil, this is the chilled water coming in. तो जब आपका part load हुआ तो क्या हुआ, कुछ water mix हो गया from the hot water side only, it gets mixed. So this valve has two inlet ports and one outlet port. One inlet port is this, one is from the coil, both mixed, and then the mixed water goes to the loop. So it is mostly used in the return line of cooling water. ये return line में लगा हुआ है देखिए. Cooling heat, it is used in return line of cooling and heating coils. There are 2 inlets and 1 outlet, and the port design is such that it cannot be used in term place of diverting valve. तो कई बार confuse होते हैं site में कि 3-way mixing valve है. It has to be seen ये क्या है, 3-way mixing valve है कि diverting valve है. क्योंकि अगर if it is a mixing valve, it has to be used in the, it cannot be used in place of diverting valve. So that thing needs to be seen. Then we also have the other type of valve is a 3-way motorized diverting valve. अब ये 3-way diverting valve जो it is put in the supply line of the valve. So this, it has basically 1 inlet and 2 outlets. तो ये bypass कर रहा है, divert कर रहा है in the return line, the chill water outline. So this is there is 1 inlet and 2 outlets, and the port design is used that it can be used in case of mixing valve. तो लेकिन normally these valves are expensive and not commonly used. अब इनके opening characteristics में there are 2-3 types of valve flow characteristics. They can be quick opening type. This can be linear. तो linear normally steam control valves में use करते हैं क्योंकि वहाँ पे heat exchange varies linearly with the flow rate. Then we can have the equal percentage where normally these are used to modulate water flow in the same proportion as the the valve is modulated. The flow is also modulated in the. So this is a quick opening. This is a linear. This is a equal percentage valve characteristic. और इसको कैसे select करते हैं? It is the 3-way valves. They are selected based on the value of CV. Normal conventional thumb rule तो है कि जो line pipe size है, 8 size छोटा है, that is the valve control valve size. But technically, the right way of doing it is by calculation of the CV value. And what is CV value? It is the quantity of water in GPM at 60 degree Fahrenheit that will flow through a given valve with pressure drop of 1 psig. तो वो उससे वो CV वैल्यू निकलती है उसकी. तो CV वैल्यू से फिर valve के there are sizing charts from the manufacturers. Based on that we can determine the size of the control valve, because CV determines the size of the control valve. Normally वही आता है. Normally the valve size is 1 size lower than the connecting pipe size, but it has to be properly sized, then only it will function properly. If the valve has to be in control, it should contribute a significant drop portion of total pressure. अब अगर आपने same size का लगा दिया pipeline और valve भी, so it will have no control. It has to have a significant pressure drop system का. So then only it will have a proper control over the system. It should be either greater than or equal to the pressure drop. जितना coil में और उसके बीच में pressure drop आ रहा है, उससे ज़्यादा या at least उसके बराबर होना चाहिए. तभी इसका one size smaller रहता है, so that the pressure drop is higher. So generally, it is equal to the pressure drop of the coil. This we talked about the control valves. Now we come to the expansion tank, which was the other part of the hydronic system. So expansion tank is a device that allows for the expansion and contraction of the water in a closed water system, so as to restrict the system pressure. So when the water temperature changes between 2 predetermined limits and filling temperature versus operating temperature, pressure of water changes. या summer में भी जब temperature change हो रहा है winters में, तो to take care of the expansion and contraction of water according to the temperature, and then during the filling of the system also, this is the point from where the system is, entire chill water system is filled. Now, this expansion tank nowadays they are coming in 2 types. One is the open type, one is a closed type. The closed type is still better because here even that minor contact with the air is not possible, and the air does not come into the system, and the corrosion of the pipelines is avoided. So open expansion tank is vented to the atmosphere. It is located in normally जो highest point होता है pipe का, उससे 3 feet above it is put. So normally on the terrace, staircase मंटी पे लगा के, and then we connect a 50 mm pipeline to the return side of the pipe. तो वहां से फिर ये it is connected. So it's connected to the suction side of the pump to prevent system water pressure drop below atmosphere. Minimum volume जो है, it should be at least 6% of the system volume. And since water surface is exposed to atmospheric oxygen, yeah, absorbed and this is less. So preferable is the closed expansion tank because it prevents the corrosion, though its cost is slightly higher than the open expansion tank. Closed expansion tank, it is a closed expansion tank. Basically, it provides excellent air venting capacity. So we should try using, like in the good system, for a good system health, we should use the closed expansion tank. So now this is again it's a system, complete hydronic system showing for the a closed system. We have the chiller. We have these are all the chillers. These are the pumps and the valves and the fittings, and we have the loads and the expansion tank. So it's a complete flow rate of the machine, temperature in, out, and chill water pumps, 3 chillers. So it's a closed chill water schematic diagram for the chill water hydronic system. This is the condenser water hydronic system. We have the condensers, again the valves, we have the condenser water pumps, and we have pot strainers, we have the cooling towers. So this is a diagram of a condenser water open hydronic system. And so that was about the piping, valves. We covered the expansion tanks. We covered the piping and the ancillaries. Now coming a bit about the pump fundamentals, which also pumps, which are a very essential part of the hydronic system. So just recapping few of the pump fundamentals. We know pump head. We are और familiar. जब select करते हैं तो दो ही चीजें देखते हैं, उसमें head कितना है, flow rate कितना है. We'll just refresh in the pump affinity laws. What is net positive suction head? What is cavitation? What is power and efficiency? तो pump head क्या होता है? आप देखिए क्या, this is the suction head. क्या source से कहाँ तक लेके जाना है? What is the source from the water, from where the water is to be transported, and what is the destination? So it is the suction, and this is the discharge. So what is the total static head the pump has to work against? It is the difference in the height between the source and the destination of the pump liquid. So it is the sum of the static suction. Static suction क्या होता है? It is the vertical distance between the center line of the pump, जो pump का center line है और level है water source का, उसके बीच का जो height है, that is the suction head of the pump. और static discharge head क्या है? It is the vertical distance between the center line of the pump and the top level to which the pump is to discharge. The vertical distance between the pump center line and surface of the liquid in the destination. This is the discharge head. So total head, when we say कि pump क्या कर रहा है? Pump it is pumping the water, it is lifting the water and taking care of the static suction head and the static discharge head. Now, what are the pump affinity laws? सब जानते ही होंगे. Q is proportional to N. That means the capacity, it varies directly as the change in speed. Head varies as square of the speed. Power is proportional to cubic times the speed. And अगर speed fixed है हमारी, तो Q is proportional to cube of the diameter of the impeller with the speed fixed. And head is proportional to square of the diameter, and BHP is proportional to D5. अब ये इसका आपको पता चलेगा अभी in the later part कि how effective it is. कि अगर हम एक बड़ा impeller use कर रहे हैं और unnecessarily throttle कर रहे हैं, तो if we trim the impeller even a bit, you know, the power उतना कितना drastically कम हो जाता है because of this relationship. The other parameter which is to be seen in the selection of the pumps is net positive suction head. तो net positive suction head का क्या मतलब है? Basically कि जो pumps हैं, they are now meant to, whenever we are selecting the pumps, we are selecting the pumps to pump water, not the vapors. क्योंकि vapor का अगर if we compare 1 cubic feet of water, इतना volume of water, it is how much volume it occupies as a vapor. It is 1700 cubic feet of vapor at the same temperature. So you can appreciate that, like pump, if it has to pump liquid effectively, it should always be in the liquid form. Vapor form में आते ही वो it will start malfunctioning. So अगर there is a rise in temperature and fall in pressure, it induces the vaporization. So pump always needs to have sufficient suction head to prevent vaporization at the lowest pressure point in the pump. तो मतलब ये है कि इसमें suction head minimum होना चाहिए. So it should be above the vapor pressure of the at the suction, and so that there is no bubble formation. और ये ऊपर ही ऊपर उसके operate करे. But if the suction pressure is less than the vapor pressure, there will be a bubble formation. So NPSH is a measure to prevent the vaporization, and the net positive suction head, the total head at the suction flange, and it should be above the vapor pressure of the liquid. Right. So this is the NPSHR is a positive head required in the pump section to overcome the pressure drop in the pump and maintain the liquid above its vapor pressure. So this is the minimum pressure required at the suction to avoid cavitation. Cavitation क्या होता है कि when there are some vapors which are generated due to the low pressure or high temperature, then it will start causing pitting in the impeller. It will reduce the service life. बहुत इसमें मतलब there will be bubbles and it will be damaging the impeller in the due course of time. So this is the cavitation. Then power and efficiency. तो pump का power जो है, this is calculated by the formula BHP is flow into head divided by 3960 into pump efficiency, and इसी से हम लोग calculate करते हैं कितना flow rate है, कितना head उसको overcome करना है, और pump efficiency determine करके 75-80%, तो we can calculate this BHP, and then above that there has to be some contingency for the losses, and select the motor. Now what should be the ideal steps for pump selection? पहले तो हमें पता होना चाहिए what is the application of the pump, use क्या है, location of the pump क्या है, determine उस end use, whether what is the flow rate required, what is the head required, कितने head के against काम करना है, what is the best possible configuration, क्या configuration ले, 1:1 ले, मतलब chiller के against या 2 ले, that तो we have to decide based on our application, और एक standby तो लेते ही हैं normally. Then review the pump range charts of the manufacturer. उसके मैन्युफैक्चरिंग की परफॉर्मेंस कर्व्स देखने बहुत जरूरी है. रिव्यू द परफॉर्मेंस कर्व्स को कैसे पढ़ना है, इसको ऐसे पढ़ते हैं कि लाइक वी नीड टू सी कि ऑपरेटिंग पॉइंट हमारा क्या आ रहा है, व्हाट इज द बेस्ट ऑपरेटिंग पॉइंट, बेस्ट बीईपी, वी नीड टू रिव्यू द परफॉर्मेंस विद रिस्पेक्ट टू दिस, कि वहां ये जो है सेंटर में आ रहा है, एज पे आ रहा है, मतलब इट शुड बी टुवर्ड्स द सेंटर, एंड उसमें हमें देखना है कि एंड ऑफ द कर्व में पावर रेटिंग क्या आ रही है, what is the HP requirement at end of the curve, वो देखना इसलिए जरूरी होता है. Like normally the systems, they are the heads are specified by thumb rules, right? So in the actual systems the heads are much more lower, so tends initially the pumps will tend to pump more water, generate more water, so that will also consume more power, तो motor burn out होने के chances होते हैं. तो for safety purpose, like it is sometimes it is specified that the motor should be sized to the end of the curve, and efficiency point भी देखना है उसका कि जो best operating point is always the best efficiency point, and the minimum noise point, minimum turbulence, no this cavitation, और NPSH भी उसमें positive मिलता है. तो this is the performance curve has to be seen accordingly. तो GPM तो हमने बताया कि how we calculate the capacity, we calculate the GPM with the this formula. फिर उसके बाद we have to when we see the manufacturer curve, we have to select the pump in the best selection zone. जैसे अगर ये हमारा पॉइंट आया है तो पंप नॉर्मली क्या करेगा कि within -1/4 and +1/4, this is the best region for operation. मतलब इतना ही डेविएशन होना चाहिए because of any pressure differentials. It should not operate beyond this because here cavitation will tend to happen, और बहुत कम पे भी नहीं होना चाहिए जितना डिजाइन फ्लो है. तो ये वाला जो रीजन है उसमें 15 to 20% ऑफ द डिजाइन फ्लो उतने रीजन में भी नहीं होना चाहिए, बिकॉज यहाँ पे क्या है कि तो फिक्स्ड लॉसेस हैं, दे आर मैक्सिमम हीट इज देयर. So it also we should not operate in this range because here input energy is converted into heat and it results in damage to the pump. So this is the best point on the performance curve from where the pump should be selected. So normally best selection range is about midpoint of the capacity curve plus or minus 1/4. And because open, when the modulating controls valves are open, they cause a shift in the actual pump operating point. जब valve को बंद या खोलते हैं तो वो इधर या उधर शिफ्ट होता है, तो बहुत ज्यादा सिलेक्शन यहाँ पे लेफ्ट में शिफ्ट होने से शट ऑफ हेड के पास आ सकता है, और उस केस में इट कॉजेज हीट डिसिपेशन एंड इट कॉजेज थ्रस्ट लोड ऑन द बेयरिंग एंड it damages the pump. और बहुत ज्यादा राइट पे करने से भी it does not has too much selection, too much to the right is no shift allowance. Operation in this area, it causes noise, it causes cavitation, it causes possible pump damage, it will also reduce the flow to the system. To select the proper curve, अब curve की दो तीन तरह के curves आते हैं pumps के. So if we analyze, there are three types of curves. There are steep curves, there are drooping curves, there are flat curves. तो अब उस पे क्या देखें, कैसे हम select करें? Drooping curves are not very favorable because they are very unstable. So जैसे you are seeing that like for one head, it has 2 points. 2 flow rates it is giving. So it is unstable. It will keep shunting between the 2 points. This is not a right curve. And preferable is, so this is a drooping curve is not to be selected. Then we have the steep curves are more stable. These are the steep curves. तो इसमें एक point पे एक ही आपको floor, एक head पे एक ही flow rate मिलेगा. So it is a, these are more stable. So we should try the pump characteristic curves should be steep. Then flat curves. Flat curves है, they are also preferred. Flat curves में क्या है कि these are preferred for the closed circuit system. क्योंकि steep में भी क्या है कि like for a small change in variation, there has to be large change in the head. But यहाँ पे ज़्यादा balancing की ज़रूरत नहीं पड़ेगी because with the small change in the system, with the small change in head, the flow rates will be changed in the capacity. So flat curves are normally used in the closed circuit systems. Now select the optimal efficiency of the pumps. So maximum efficiency occurs at the best efficiency point, which is the operating point. There is one particular point within the range on the pump curve where the efficiency will be maximum. Or जैसे ही we deviate left or right from that best operating point, it will be efficiency will reduce in both the cases. And the efficiency, it also depends on the impeller and the volute design. तो अब इसमें हम कैसे suitable casing और impeller कैसे select किया जाए? Now, एक casing जो pump की होती है, it can accommodate a set of 3 to 4 impellers. 3 से 4 तरह के impeller वो sizes hold कर सकता है. तो अभी आपको एक मैन्युफैक्चरर देता है, आपको पहले ही ये वाला साइज देता है, तो आप उसको सबसे पहले छोटा देता है तो आप उसको बड़ा नहीं कर सकते. तो जो बेस्ट होता है कि we should neither select the maximum nor select the minimum diameter, select an intermediate. आप देखो कि आपका जो ऑपरेशन पॉइंट है वो मिडल वाले पे सिलेक्टेड हो, बिकॉज मैक्सिमम डायमीटर अगर लेंगे तो इफ impeller diameter has to be increased, अगर आप बढ़ाना चाहते हो, you cannot change the impeller in the pump and pump has to be changed. If it is minimum diameter तो आप उसको ट्रिम नहीं कर सकते, and because trimming से आप बैलेंसिंग का रिक्वायरमेंट कम कर सकते हो. तो अगर इस पे सिलेक्शन किया है तो दैट यू कैन नॉट डू, यू डोंट हैव द फ्लेक्सिबिलिटी. सो ऑलवेज ट्राई टू select the pump at the intermediate impeller dia. Then selection of the non-overloading motor with an overestimated head. तो जैसे I was saying कि thumb rule से ले लेते हैं and then they say कि motor चलो बड़ी लगा देंगे, so we are safe. But normally फिर क्या होगा कि if the head is less, we are going for the non-overloading motor, it is always too oversized. तो जब वो actual operating point पे चलेगी तो it will run at lower efficiency. So it is better that we estimate the head correctly. Now selection of RPM. Best efficiency point moves towards the right with increase in RPM. जैसे ही हमारा RPM बढ़ता है तो best efficiency point बढ़ जाता है, right पे आ जाता है, which is not a stable zone. So the above 3000 RPM is not recommended for the pump hydronic systems, right? And pump efficiency for the larger pumps is higher, and because आपके internal losses तो fixed रहते हैं, तो जितना बड़ा pump होगा उतना ज़्यादा efficient होगा. तो you should, while selecting the pumps, we should aim for higher efficiency अगर हमारे बड़े size के pumps हैं. Then check for the hydraulic turbulence. तो यहाँ पे जो maximum efficiency point है, that is also the point of minimum shaft deflection. There the pump is operating very stably. There the hydraulic turbulence is minimum, shaft deflection is minimum. So इससे ऊपर जब इधर जाते हैं तो there is a lot of hydraulic turbulence. There is a lot of energy lost due to this. This is the maximum energy point, and on the right side also of this there is an energy loss due to the hydraulic turbulence. So again, the best operating point is also the point of minimum hydraulic turbulence. So now few energy efficient opportunities, what are the design, operation and maintenance strategies we can follow for optimizing the energy efficiency through the operating the pumps. Select the right pump, control the flow rate by speed variation. तो आप इसमें हम VFD लगाना अच्छा है. Pumps should be in parallel to meet the varying demands. Eliminate the flow control valve. Eliminate the bypass. Bypass ना लगाएं, it's a waste of energy. और start stop control of pump हो हमारे पास impeller trimming के option हो rather than modulating after commissioning. If we find that the flow rates generated are higher, we can think of trimming the impeller rather than throttling the valve. So oversized pump, it will require the flow control, and we have to provide additional head or additional head करने से सिस्टम भी लेफ्ट में हमने जैसे देखा कि वो शिफ्ट हो जाएगा, उसकी एफिशिएंसी भी कम हो जाएगी. तो ओवरसाइज पंप इज नॉट really preferable. So already if the pump is purchased, then go for a VSD, go for reducing the RPM to the VSD, or go for a trimming of the impeller. So that will reduce your pumping cost. Because effect of speed, you have already seen the power is proportional to the cubic relation with the RPM. So if the speed is reduced by 1/2, power is going to reduce by 1/8. So with the variable speed drive, you can do this. Or then impeller trimming. तो अगर आपका जैसे ये था आपका impeller was the original selected. This is the pump performance using the original impeller. So pump is originally serving at this point of the system curve. So once you trim it, after trimming, this is the size of the impeller. After trimming it, how the pump the desired flow you are getting, and the pump serves at this point, and you get the desired flow. Pump efficiency will improve. There is not much deviation from the initial operating point. Efficiency will remain intact and the power consumption will reduce. So 2% reduction in impeller diameter causes 2% reduction in flow, but 4% reduction in head and 8% reduction in power. So it is always better to go for impeller trimming if required. But the limitation is that it should not be reduced below 70% of the original size. And in some pumps, it may also cause, it has to be seen that the pump's NPSHR requirement has to be seen, and minimum flow requirement of the flow also may be disturbed. So all those things have to be checked before going for impeller trimming. So the improving pump efficiency, some more thing, that pumps, they are consuming 10 to 12% power in HVAC system. So they need to have high efficiency and keep the fluid velocity in the pipe sizing less than 4 FPS, and try to slightly oversize the pipe, because that is only a peanut increase in the initial cost, but it is reducing the overall system pressure drop and the pumping energy. And keep the differential up. Proper differentials should be kept. Chill water, 10 degree Fahrenheit, 2.4, we can go for 12. To reduce for the high capacity systems, we can go for 12 degree Fahrenheit. So it results in almost 50% savings in the chill water power. It also reduces the sizes of the pumps, piping, and the accessories. So, and keep the piping system simple, ज़्यादा zigzag और ज़्यादा वो उसमें fittings वगैरह लगा के, it all increases the system pressure drops. Minimize the unnecessary valves or the turns and the transitions and the flow control devices. Try wherever the radiuses are there, pump change of radius should be long radius instead of a short perpendicular bends. Provide pipe supports. तो pipe supports जहाँ पे भी हमारे connections होते हैं, तो I go to sites, I see normally उसको support नहीं किया जाता. तो it is always better that the pipe weight with water is substantial. They should be supported particularly at the pump outlets, condenser outlets, so that the weight is not transferred to the pump flange. Pump के flanges में भी उसके नीचे भी support देना चाहिए. Provide support under the elbows on the pump suction and discharge. Specify efficient pumps. Specify premium efficiency motors. Provide 5 straight pipe diameter at the pump inlet connection. Provide isolation valves वगैरह देने चाहिए, so that strainer can be strained, it can be cleaned, maintained frequently. Provide line size isolation valves and check valves on the pump discharge. Provide valves on each branch and riser. Risers में भी isolation वगैरह देनी चाहिए, so that we can clean the system and balance. And try using pressure independent control valves to eliminate the need of throttling. Use variable flow configuration and review variable flow pumping option for primary instead of only primary secondary. So variable primary can be also considered. Operate the pumps near their best operating point. Ensure NPSH is available at the site of installation. Modify pumping and pump losses to minimize throttling, and ensure that all the basic instruments, pressure gauges, flow meters are available in the system, and adapt to wide load variation variables, speed drives, repair the seal and packing. This comes in the maintenance. Balance the system properly to minimize the flow and reduce the power consumption. And जो मल्टीपल पंप ऑपरेशन है उसमें प्रॉपरली उसको देखना चाहिए पैरेलल पंपिंग के लिए हाउ दे आर working in the combined system, and replace the old pumps with the energy efficient pumps, or to improve the earlier existing oversized pumps, use VFDs or downsize, replace impeller or replace with the smaller, reduce the system resistance, and regularly check for the vibration. Then last part of this, I'm just touching upon the various type of chill water distribution schemes which are followed. So we have the constant flow chill water system. We have the primary, secondary constant flow chill water system. We have the constant primary, variable secondary chill water system. And we now also have variable primary chill water system. So constant flow chill water system, we are all familiar with this system where we have the chillers and the pumps are constant speed, and we have the loads. There we use the three-way valves. So constant speed, they distribute same quantity of water at all the times, and system uses three-way valves to bypass or mix the water, and total water quantity returned to the chiller remains same, but it has high power consumption because the pumps keep running at the same speed irrespective of the load. Then you can have the second system is the constant flow primary and secondary chill water system. So this is where the primary and the secondary circuits are decoupled, but the secondary is also not variable. So basically, if there are different blocks or different zones, we have different secondary pumps serving those zones. So we can just, accomplish some power consumption is there by riding the curves, but there is no speed variation. So constant speed primary secondary also distribute the chilled water, and these are the primary pumps. They will take care of the pressure drop in the chiller and in the pipes and the valves in the primary loop, and secondary pumps, they take care of the secondary, that load as well as the distribution piping and the coils, and they use three-way mixing valves for mixing or bypassing, and again the total return water to the system chiller remains same. And here we can only advantages, we can allow the different chill water rates and delta T on the different secondary loops. Then we have the constant primary variable flow secondary, which is the most common system prevalent. So here we have the constant speed primary, again, which is taking care of the pressure drop in the chiller and the primary loop piping, etc. So secondary pumps are also provided with a variable speed drive. So here we have a differential pressure sensor, which keeps on sensing as the loads keep on varying. They two-way valves, they push back the water in the supply line, and the differential pressure between the supply and the return header goes on increasing, and based on the signal, it gives to the variable speed drive of the secondary pump to reduce the speed and the load in the power consumption in the secondary pump, it reduces. So it is an energy efficient operation. Then we have the primary, secondary, tertiary flow systems. So here we have basically the chiller plant room has the primary loop and the secondary loop. And the tertiary, suppose it's a district cooling system, we have different buildings, building 1, 2, 3, 4. Then this secondary piping is running cross country and then distributing to each of the building. So zones are divided, so we get more energy efficiency. So this is the secondary loop. If it is coming, it is also variable flow based on the differential pressure. It gives the signal to the secondary pump controller, and then for that particular vertical tower, we have the tertiary pump. So it takes care, again, it is a variable tertiary. So it will modulate the water depending on that block requirement. And then latest is the primary variable flow, which also have become prominent. There we can even change the flow in the chiller up to a specified range as permitted by the manufacturer. It has to be compatible with that. So we have the primary, there is a one set of pumps only, which is a primary variable. And through this, we can give the signal to the chiller. We can reduce the water flow rate in the circuit. So that was all I had to share on the hydronic systems. So I think it will be of use to you. At least we could refresh on some fundamentals of piping and hydronic system. Thank you so much for hearing.
Thank you very much, ma'am, for your kind presentation. I think it was one of the best presentation, I would say. And if anybody have question, you can share in the Q&A section. We'll take it one by one. We'll wait for 2 minutes. I think, ma'am, a few questions has been asked, and you
Yeah.
answered is very well. And if I mean, if anybody have more question,
You can mail it to me
yeah,
anytime.
yeah,
So you'll get the replies.
okay. So I think now we are end of this two session. First one is covered, that is on enabling healthcare facilities to operate in carbon neutral future. Second one is on piping and hydronic system. As this program is organized by Delhi chapter of ISHRAE, supported by Women ISHRAE, and is sponsored by Fusion Pipes and Fittings. We are thankful to Fusion Pipes and Fittings, and of course, we are thankful to you, ma'am, for your presentation is always nice as usual.
Thank
So,
you so much.
I mean, you are the great pillar in terms of workshop and all,
My
connecting
pleasure.
and knowledge sharing program, as ISRE has the basic theme to share knowledge, disseminate knowledge. And you kind of people are supporting very well. You are giving your times and all. So apart from this, I request one who is non-member of ISRE, please join us to boost our society in terms of your knowledge and your experience. And again, we are thankful for Fusion pipes and fittings for supporting this. Anything we would like to share, Pushpender sir, in this forum?
मैं इतना ही कहना चाहूंगा कि 3 घंटे सुनने में इतना पेशेंस लगता है, उस कंटिन्यूअसली मैडम 3 घंटे से कंटिन्यूअसली बोल रही थी, तो बहुत ही डिफिकल्ट, मतलब बहुत ही मेहनत की होगी उन्होंने इस प्रेजेंटेशन को बनाने में, और इतना कंटेंट था प्रेजेंटेशन में, तो मैं दिल की गहराइयों से मैं इनको थैंक कहना चाहता हूँ। उन्होंने बहुत ही मेहनत से मतलब प्रेजेंटेशन बनाई। थैंक यू।
Thank you so much, Pushpender ji.
Thank you, Pushpender sir, for your kind words for this program, and definitely we'll make this kind of programs in near future as well. So thank you very much, ma'am. On behalf of all the committee from the sponsor side and all the team what we have, we are thankful to you, and we are thankful to all the audience for joining this program. So thank you very much. With this note, I would like to close the session.
Thank you so much. Goodbye.
Thank you.
Thank you.